You open your eyes in the morning and for just a moment you can feel the dream. It's vivid, strange, maybe even meaningful. But by the time you're brushing your teeth, it's gone, completely vanished as if it never happened at all. Why does the brain let go of dreams so quickly? The answer lies in how your brain shifts gears between sleeping and waking. During REM sleep, the stage where most vivid dreaming occurs, your brain is incredibly active. It's processing emotions, running through scenarios and creating narratives that often feel bizarre or nonsensical. But here's the key detail. While all this is happening, the part of your brain responsible for forming long-term memories, the hippocampus, isn't working the same way it does when you're awake. Think of your brain during REM sleep as a theater where the show is happening, but no one's recording it. The experience is real in the moment, but there's no mechanism actively saving it to your mental archive. When you wake up, your brain rapidly transitions from this dream state to waking consciousness. Neurochemicals shift. Norepinephrine and serotonin, which are suppressed during REM sleep, flood back into your system. This chemical change essentially wipes the slate clean. Dreams are stored in what's called short-term or working memory, the same place you might hold a phone number someone just told you. If you don't actively repeat that number or write it down, it fades within seconds. Dreams work the same way. Unless you consciously focus on them immediately after waking, rehearsing the details in your mind or writing them down, they dissolve like mist in sunlight. There's also a structural reason for this fragility. During sleep, the prefrontal cortex, the part of your brain that handles logic, planning, and memory encoding, is far less active. Without this region fully online, your brain isn't prioritizing the task of converting dream content into lasting memories. It's as if the dream exists in a temporary file that gets deleted the moment your brain needs the space for something else. The transition from sleep to wakefulness is abrupt. One moment you're in a dream world where the rules of reality don't apply. The next, you're back in your bedroom and your brain is already shifting focus to the day ahead. That shift happens so fast that dreams, which were never firmly anchored in memory to begin with, simply don't make the cut. They're overwritten by the immediate needs of waking life. Checking the time, feeling hungry, planning your morning. Some people remember dreams more than others, and that often comes down to when they wake up. If you wake naturally during or just after a REM cycle, you're more likely to hold onto fragments of the dream. But if you're jolted awake by an alarm during deep sleep, the dream is usually gone instantly. The brain hasn't had a chance to even temporarily hold on to it. Interestingly, the dreams you do remember tend to be the ones tied to strong emotions. Fear, joy, confusion. These emotional tags give the brain a reason to flag the dream as something worth keeping, at least for a little while. But even then, without reinforcement, the memory fades. Dreams aren't designed to be remembered. They're designed to be experienced, processed, and released. The brain treats them as mental rehearsals, emotional regulation, or random neural activity, not as events that need to be archived. So when you lose a dream within minutes of waking, your brain isn't malfunctioning. It's working exactly as intended, prioritizing what matters for survival and daily function over the fleeting, fragile narratives of the night. You set your alarm for 7 a.m., but you wake up at 6:58, wide awake. No grogginess, no confusion. Just your eyes opening naturally, 2 minutes before the alarm even goes off. It happens more often than it should, and it feels almost like a strange superpower. But how does your body know? The answer lies in your circadian rhythm, your body's internal clock. This isn't some vague metaphor. It's a real biological system that operates on a roughly 24-hour cycle, regulating when you feel awake, when you feel sleepy, and how your body prepares for transitions between the two. This clock is located in a tiny region of your brain called the suprachiasmatic nucleus, or SCN, which sits just above where your optic nerves cross. It's constantly receiving input from your environment, especially light, to keep your internal sense of time aligned with the outside world. But here's where it gets more interesting. Your circadian rhythm doesn't just respond to light. It also tracks patterns. If you consistently wake up at the same time day after day, your brain begins to anticipate that moment. About an hour before your usual wake time, your body starts preparing. Your core body temperature, which drops during the night, begins to rise. Your sleep becomes lighter, moving out of the deeper stages and into lighter REM or stage 2 sleep. And critically, your body starts releasing cortisol. Cortisol often gets a bad reputation as the stress hormone, but in the morning it plays a crucial role. This release, called the cortisol awakening response, is your body's natural wake-up call. It peaks within the first 30 minutes after waking, giving you energy and alertness. But the process doesn't start when you open your eyes. It starts before, ramping up in anticipation of the moment you typically wake. Your brain has learned your schedule. If you wake at 7 a.m. most days, your internal systems begin the waking process around 6 a.m. or earlier. By the time 7 a.m. arrives, your body is already primed. So when you wake just before the alarm, it's not luck or coincidence. It's your brain's prediction playing out perfectly. You've trained it, often without realizing, and it's following the script. This ability to anticipate time isn't limited to waking. Your body does this throughout the day. If you eat lunch at the same time every day, your stomach starts producing digestive enzymes in advance. If you exercise at the same time, your body begins preparing your muscles and cardiovascular system beforehand. The brain is constantly running predictions based on patterns, and sleep is no exception. There's also a psychological component. If you're someone who hates being startled awake by an alarm, your brain might actually heighten its vigilance as the expected wake time approaches. It's as if your subconscious is monitoring the clock, trying to avoid the unpleasant jolt. This is why people who are anxious about missing an important morning event often wake up earlier than planned. The brain prioritizes the anticipated need over sleep depth. Interestingly, this system can be disrupted. If your sleep schedule is irregular, if you go to bed and wake up at different times every day, your circadian rhythm struggles to form a reliable pattern. The anticipatory mechanisms don't kick in as effectively, and you're more likely to sleep through alarms or wake up feeling disoriented. Consistency is what makes the system work. The body's ability to wake itself isn't magic. It's biology fine-tuned by repetition. Your brain, your hormones, and your internal clock all work together, tracking time in ways you're not consciously aware of. And when everything aligns, you wake naturally, calmly, just before the alarm has a chance to shatter the silence. When you're a child, summer vacation feels endless. A single day can stretch on forever. But as an adult, entire years seem to slip by in a blink. Holidays arrive faster than expected, birthdays feel more frequent, and time, in general, just doesn't last the way it used to. It's not your imagination. Time genuinely feels like it accelerates as you age, and there are real psychological and neurological reasons for this. One of the most compelling explanations is the proportional theory of time perception. When you're 5 years old, 1 year represents 20% of your entire life. That's a massive chunk of your existence, and your brain processes it as such. But when you're 50, 1 year is only 2% of your life. Proportionally, it's much smaller, and your brain treats it that way. Each passing year becomes a smaller fraction of your total experience, so it feels less significant, less lengthy. Time isn't actually speeding up, but your perception of its weight is shifting. But there's more to it than just math. The way your brain encodes memories plays a huge role in how you experience the passage of time. When you're young, almost everything is new. You're learning constantly. Your first day of school, your first time riding a bike, your first trip to the ocean. Each of these experiences creates vivid, detailed memories because they're novel. Your brain pays attention to new information, encoding it deeply. When you look back on your childhood, you have a dense collection of memories, and that richness makes it feel like a long period. As you age, novelty decreases. Your daily routine becomes predictable. You drive the same route to work. You eat similar meals. You see the same people. Your brain, efficient as always, stops paying as much attention to these repetitive experiences. Why waste energy encoding the 500th time you made coffee the same way? So it doesn't. These experiences pass through your consciousness, but they don't get stored as distinct memories. When you look back on a month or a year, there are fewer memorable markers, fewer distinct moments. The time feels compressed because your brain didn't bother to record much of it. This is why vacations or major life changes make time feel slower. When you travel to a new place, try a new hobby, or go through a significant transition, your brain snaps back into high encoding mode. Suddenly, you're creating new memories again, and those memories make time feel more substantial. A week-long trip to a foreign country can feel longer than a month at home doing the same routine because your brain has more to hold onto. There's also a metabolic factor. As you age, your brain's processing speed subtly changes. Children's brains are in overdrive, forming new neural connections at a rapid pace. Everything is being absorbed, analyzed, and stored. But adult brains, while still highly capable, aren't in that same hyper-learning mode. The subjective experience of time is tied to how much mental activity is happening. When your brain is processing more information, time feels slower. When it's on autopilot, time flies. Routine is the enemy of time perception. The more automatic your life becomes, the faster time seems to pass. This is why people often say that childhood felt long but adulthood feels short. Childhood is full of firsts. Adulthood, unless you actively create novelty, is full of sameness. The good news is that you can influence this. By intentionally seeking new experiences, breaking routines, and staying curious, you can slow down your subjective experience of time. It won't stop the calendar from moving, but it will give you more moments worth remembering. And those moments, those memories, are what make time feel real. You walk into a room and suddenly you're hit with an overwhelming sense that you've been here before. Not just the room itself, but this exact moment. The way the light is hitting the wall, the person standing near the window, even the thought you were just having. It all feels impossibly familiar, like a memory you can't quite place. Then, just as quickly as it came, the feeling vanishes. You've just experienced déjà vu, and it's one of the strangest sensations the brain can produce. Déjà vu, French for already seen, is the eerie feeling that a new experience is actually a repetition of something you've lived through before. It happens to most people at least once in their lives, and for some, it's a regular occurrence. But despite how common it is, the brain mechanism behind it is still somewhat mysterious. What we do know, though, paints a fascinating picture of how memory and perception can misfire. One of the leading theories involves the temporal lobes, particularly the hippocampus and the surrounding structures that handle memory processing. These areas are constantly working to distinguish between what's happening now and what happened in the past. When you experience something new, your brain encodes it as a fresh memory. But sometimes, there's a tiny glitch. The brain processes the current experience through two pathways, one for perception and one for memory. Normally, these pathways work in sync. You see something, and your brain knows it's new. But occasionally, there's a split-second delay. The memory pathway fires just a fraction faster than it should, tagging the experience as familiar before the perception pathway fully registers it as new. Think of it like a recording being played back to you while it's still being recorded. The brain gets confused. It recognizes the moment, but it shouldn't because the moment is still happening. That confusion creates the sensation of déjà vu. It's not a real memory. It's a memory-like signal applied to the present. Another explanation involves pattern recognition. Your brain is constantly matching what you see and feel to stored patterns from past experiences. Most of the time, this happens unconsciously. You don't actively think, "This room reminds me of my grandmother's house," but your brain might make that connection below the surface. If the current environment shares enough similarities with a past memory, vague shapes, lighting, sounds, smells, your brain might flag it as familiar without giving you access to the specific memory it's pulling from. The result? A feeling of recognition without context. You know you've seen this before, but you can't pinpoint when or where. There's also evidence that déjà vu is more common in people with highly active imaginations or those who travel frequently and encounter varied environments. The more experiences you have, the more patterns your brain has stored, and the more opportunities there are for these wires to cross. Stress and fatigue can increase déjà vu as well, likely because the brain's filtering systems aren't operating at full efficiency. Interestingly, certain neurological conditions like temporal lobe epilepsy can cause frequent and intense déjà vu. In these cases, abnormal electrical activity in the brain's memory centers creates the sensation repeatedly. But for most people, déjà vu is harmless, just a brief, strange moment where the brain's timing gets a little off. The sensation usually lasts only a few seconds, but it can feel much longer because your brain is actively trying to resolve the contradiction. You're searching for the memory that isn't there, which intensifies the strangeness. Once your brain realizes there's no actual match, the feeling fades, and you're left with nothing but the odd aftertaste of familiarity. Déjà vu reminds us that our experience of reality is a construction. What we perceive as the present moment is actually a tiny delay, a carefully assembled version of reality built by our brain. And sometimes, just sometimes, the construction process reveals its seams. It starts innocently enough. You hear a song on the radio, maybe just a few seconds of it. Then you go about your day, but the melody won't leave. It loops in your mind, playing over and over, sometimes for hours. You try to think about something else, but the song keeps pushing its way back in. Why does this happen? Why does your brain insist on replaying the same musical snippet endlessly? The phenomenon is called an earworm, and it's more common than you might think. Studies suggest that nearly everyone experiences this at some point, and certain songs are far more likely to get stuck than others. The ones that burrow into your brain tend to share specific characteristics. They're upbeat, they have a repetitive structure, and they often include unexpected intervals or rhythmic quirks that make them slightly unusual but still catchy. The reason earworms happen lies in how your brain processes music. When you listen to a song, your auditory cortex, the part of your brain that handles sound, becomes active. But music doesn't stay isolated in that one region. It spreads. The brain links melodies to emotions, memories, and even motor control. That's why you might tap your foot or nod your head without thinking. Music engages multiple systems at once, and that widespread activation is part of why it's so sticky. But here's the key issue. The brain doesn't like unfinished patterns. If you hear part of a song, especially if it's interrupted or if you don't hear the resolution, your brain tries to complete it. This is related to something called the Zeigarnik effect, which describes how people remember incomplete tasks better than completed ones. Your brain holds on to the unfinished melody, running it in the background, attempting to bring it to a satisfying conclusion. The problem is, the loop often doesn't include the resolution. It's just the catchy bit, the hook, the chorus. So your brain keeps playing it, hopping to finish what it started, but it never quite gets there. Repetition also plays a role. Songs with repetitive structures are easier for your brain to encode. Once a melody is encoded, it takes less effort to replay it than to think about something else. It becomes the path of least resistance. Your brain, when it has a spare moment, defaults to the loop because it's already there, already running in the background. It's like a mental screensaver. There's also an element of distraction involved. Earworms tend to appear when you're doing something that doesn't require full mental focus. Walking, driving, doing chores. Your conscious mind is occupied, but not fully, so the auditory cortex fills the gap with the most recent or most prominent melody it has stored. The song isn't really stuck. Your brain is just using it as mental filler. Interestingly, earworms are more likely to occur if you're tired, stressed, or in a particular mood. Your brain's filtering mechanisms weaken when you're fatigued, making it harder to suppress repetitive thoughts, including musical ones. Anxiety can also trigger earworms because the brain, when anxious, tends to fixate on loops and patterns as a way of seeking control. So how do you get rid of an earworm? The strategies vary. Some people find that listening to the full song helps because it gives the brain the resolution it's looking for. Others distract themselves with a different song, essentially replacing one loop with another. Some simply wait it out, letting the brain tire of the repetition on its own. Engaging in a task that requires full mental focus, like a puzzle or a conversation, can also help by redirecting your brain's attention. Earworms aren't harmful. They're just a quirk of how the brain handles music. Your auditory cortex is powerful, and music, because of its structure and emotional resonance, has a unique ability to lodge itself in your mind. The loop might be annoying, but it's also a testament to how deeply music connects with the way we think, feel, and remember. You're given a pill. You're told it will ease your pain, help you sleep, or reduce your anxiety. You take it, and within a short time, you actually feel better. The pain dulls, sleep comes easier, the anxiety lifts. But here's the twist: the pill contained nothing. No active ingredient, no chemical designed to interact with your body. It was a sugar pill, a placebo, and yet it worked. Not because you were fooled, but because your brain created real, measurable changes in your body based purely on expectation. The placebo effect is one of the most fascinating and misunderstood phenomena in medicine. For a long time, it was dismissed as mere trickery or psychological self-deception. But modern research has revealed something far more interesting. Placebos don't just make you think you feel better. They actually trigger biological processes that produce real effects. Pain decreases. Inflammation reduces. Brain chemistry shifts. The body responds to belief as if belief itself were medicine. The mechanism starts in the brain. When you expect relief, whether from a pill, an injection, or even a fake surgery, your brain activates specific pathways associated with that expectation. If you believe pain will decrease, your brain releases endorphins and other natural painkillers like dopamine. These aren't imaginary chemicals. They're the same substances your body produces during exercise or moments of pleasure. The expectation alone is enough to trigger their release, and once they're in your system, they interact with pain receptors, genuinely reducing the sensation of discomfort. This is why placebos can work even when people know they're taking a placebo. In some studies, patients were told explicitly that they were receiving a sugar pill with no active ingredients, yet many still reported improvement. The knowledge didn't erase the effect because the brain isn't just responding to deception. It's responding to the ritual, the context, and the expectation embedded in the act of treatment. Taking a pill, seeing a doctor, following a routine, all of these behaviors signal to the brain that healing is supposed to happen. And the brain, remarkably, often obliges. The placebo effect is strongest in conditions where the brain plays a significant role in symptom perception. Pain, fatigue, depression, anxiety, nausea, these are all areas where expectation can create substantial change. That's not to say these conditions are all in your head in a dismissive sense. It means the brain has real influence over how these symptoms are experienced and regulated. When the brain expects improvement, it adjusts neurotransmitter levels, alters pain thresholds, and modulates immune responses accordingly. There's also a social component. The interaction with a healthcare provider, the reassurance, the empathy, all of this enhances the placebo effect. Studies have shown that placebos work better when given by a doctor who is warm and attentive compared to one who is cold and detached. The relationship itself becomes part of the treatment. Trust, context, and expectation all feed into the brain's response. Interestingly, the opposite can also happen. If you expect a treatment to cause side effects, your brain can produce those too. This is called the nocebo effect. People given a placebo but warned about potential nausea or headaches often develop those exact symptoms. The brain's power to influence the body runs in both directions, positive and negative. Placebos don't work for everything. They won't shrink a tumor or cure an infection. They're not a replacement for real medicine when real medicine is needed, but they reveal something profound about the mind-body connection. The brain isn't just passively receiving information from the body. It's actively shaping how the body functions, how pain is felt, how healing is experienced. What makes the placebo effect so compelling is that it's not about weakness or gullibility. It's about the brain's extraordinary ability to regulate internal states based on context and expectation. Belief, in this case, isn't just a mental state. It's a biological trigger, and the body listens. You're sitting in a quiet room. Someone across from you yawns, a slow, open-mouthed stretch of the jaw. Within seconds, you feel it. The urge creeps up, undeniable. Your own jaw opens, your breath deepens, and you yawn too. You didn't plan it. You didn't even think about it. It just happened. Why does watching someone yawn make you yawn? Contagious yawning is a behavior that crosses cultures, species, and even ages. It's not limited to humans. Dogs, chimpanzees, and other social animals do it too. And the fact that it happens automatically, without conscious thought, suggests something deeper is at play. The leading explanation involves mirror neurons, specialized brain cells that activate both when you perform an action and when you observe someone else performing that same action. Mirror neurons were first discovered in the 1990s, and they've since become central to understanding empathy, imitation, and social bonding. When you see someone smile, your mirror neurons fire as if you're smiling too. When you watch someone pick up a cup, the same neurons that would activate if you were picking up the cup light up in your brain. This neural mirroring is how you understand and predict other people's actions. It's also why emotions can feel contagious. If someone near you is anxious, you might start to feel anxious too, even if nothing in your own environment has changed. Yawning fits into this same system. When you see someone yawn, your mirror neurons simulate the action internally. Your brain essentially practices yawning by activating the same motor pathways that would be used if you were yawning yourself. And sometimes, that simulation is enough to trigger the real thing. The boundary between observing and doing blurs and your body follows through. But mirror neurons alone don't explain everything. Contagious yawning is more likely to happen between people who have a close relationship. You're more likely to yawn if a friend or family member yawns compared to a stranger. This suggests that empathy plays a role. The stronger the social or emotional connection, the stronger the mirroring response. Your brain is more attuned to people you care about, and that heightened attention makes contagious behaviors more likely. Interestingly, contagious yawning doesn't appear in very young children. Infants and toddlers yawn plenty, but they don't catch yawns from others until around age 4 or 5, which is roughly when empathy and theory of mind, the ability to understand that others have thoughts and feelings, begin to develop. This timing supports the idea that contagious yawning is linked to social cognition. There's also a theory that contagious yawning serves a group function. In social animals, synchronized behaviors can strengthen group cohesion. If everyone in a group yawns around the same time, it could signal a collective shift in state, like transitioning from activity to rest. In early human groups, this kind of behavioral synchronization might have helped coordinate sleep schedules or other group activities. It's speculative, but it fits with what we know about how social species use behavioral cues to stay aligned. Some people are more susceptible to contagious yawning than others. Highly empathetic individuals tend to catch yawns more easily. People on the autism spectrum, who often process social cues differently, are less likely to yawn contagiously, which further supports the link between yawning and social emotional processing. You can even catch a yawn from reading about yawning. Right now, there's a decent chance you've yawned or felt the urge to yawn just from engaging with this topic. That's because your brain doesn't need to see an actual yawn to activate the relevant pathways. Simply thinking about yawning, or imagining it, can be enough to trigger the response. The power of suggestion taps into the same neural networks as direct observation. Contagious yawning is a small but telling example of how deeply connected we are to the people around us. Our brains are constantly monitoring, mirroring, and responding to social cues, often without our awareness. A yawn isn't just a yawn. It's a thread in the larger web of empathy and social bonding that ties us together. You're about to make a decision. Maybe it's accepting a job offer, trusting someone new, or choosing between two paths. Logically, you can't pinpoint why, but something inside you feels off. Or maybe it feels right. It's not a thought, not exactly. It's deeper, more visceral. A sensation in your stomach, a tightness, a pull. People call it a gut feeling, and it turns out that phrase is more literal than metaphorical. Your gut, the entire digestive system, is lined with an extensive network of neurons, about 100 million of them. This is called the enteric nervous system, and it's sometimes referred to as the second brain. It operates semi-independently from your central nervous system, meaning it can function without direct input from your brain. It controls digestion, nutrient absorption, and gut motility on its own. But it's also in constant communication with your actual brain, sending signals back and forth through the vagus nerve, a long, wandering nerve that connects the brainstem to the abdomen. Here's where it gets interesting. The gut doesn't just send information about digestion. It sends information about your emotional and physiological state. When you're anxious, your gut knows. When you're excited, it reacts. And critically, the gut can process certain types of information before your conscious brain even registers it. This is why gut feelings often arrive as sensations rather than thoughts. The body is responding to cues, patterns, or threats that your conscious mind hasn't fully analyzed yet. When you encounter a situation, your brain and your gut are both processing it, but in different ways. Your brain handles logic, language, and deliberate reasoning. Your gut, through the enteric nervous system, taps into something more primal. It's tracking subtle signals, changes in heart rate, shifts in muscle tension, even variations in your environment that you're not consciously noticing. These signals get filtered through the vagus nerve and influence how you feel, often before you know why. This is why gut feelings can be so accurate. They're not random. They're based on real data, just data that hasn't made it to your conscious awareness yet. Your body is picking up on patterns, drawing from past experiences stored in implicit memory, things you learned but didn't explicitly memorize. If you've been in a similar situation before, even if you don't remember it consciously, your gut might recognize the pattern and signal caution or encouragement. There's also a chemical component. Your gut produces neurotransmitters, including serotonin and dopamine. In fact, about 90% of the body's serotonin is made in the gut, not the brain. These chemicals influence mood, decision-making, and emotional regulation. When your gut is in distress, it can affect your mental state. When it's functioning smoothly, you tend to feel more stable. The gut-brain axis, the bidirectional communication between these two systems, means that what happens in your stomach genuinely affects how you think and feel. Stress is a perfect example. When you're stressed, your brain signals the gut through the vagus nerve. The gut responds by altering its activity, slowing digestion, increasing acid production, or triggering that familiar butterfly sensation. But the reverse is also true. If your gut is unhealthy, inflamed, or dealing with poor diet, it can send distress signals to the brain, contributing to anxiety, depression, or brain fog. Gut feelings are also shaped by intuition, which is essentially rapid, unconscious pattern recognition. Your brain has stored countless experiences, and when faced with a new situation, it quickly scans for matches. If something feels familiar in a negative way, your gut might tighten up. If it feels safe or promising, you might feel a sense of ease. This isn't magic. It's your brain and body working together, using all available information, conscious and unconscious, to guide you. Not every gut feeling is right. Sometimes anxiety or past trauma can create false alarms, but more often than not, especially in situations involving people, environments, or decisions you have experience with, your gut is picking up on something real. It's your body's way of communicating. I've processed the data, and here's what I think. The challenge is learning to distinguish between a genuine gut instinct and fear or overthinking. Trusting your gut doesn't mean ignoring logic. It means recognizing that your body has its own intelligence, its own way of interpreting the world. And sometimes, that interpretation arrives before your conscious mind has caught up. You can tickle someone else easily. A quick poke to the ribs, a light brush on the sole of the foot, and they'll squirm, laugh, maybe pull away. But try the same thing on yourself. Nothing. No matter how lightly you touch, no matter where, the sensation just isn't there. Why can't you tickle yourself when the same touch from someone else would make you flinch? The answer lies in how your brain predicts and filters sensory information. Every time you move, your brain creates an internal model of what that movement will feel like. This prediction happens in the cerebellum, a region at the back of your brain that coordinates movement and sensory input. Before your hand even makes contact with your skin, your cerebellum has already calculated what the touch will feel like, when it will happen, and how intense it will be. This prediction is incredibly precise, and it allows your brain to filter out sensory information that's self-generated. This filtering system exists for a good reason. Imagine if every time you walked, you felt the full sensation of your clothes rubbing against your skin, or if every time you swallowed, you were acutely aware of the feeling in your throat. Your brain would be overwhelmed with irrelevant sensory data. So instead, it cancels out expected sensations, turning down the volume on anything it knows is coming. This is called sensory attenuation, and it's why you don't constantly feel your tongue in your mouth or notice the weight of your shirt unless something changes. Tickling relies on the element of surprise. When someone else touches you, your brain doesn't have a prediction for it. The touch is external, unexpected, and your sensory system responds at full intensity. The unpredictability of where and when the touch will happen is what makes it ticklish. Your brain can't cancel the signal because it didn't generate the signal in the first place. Researchers have tested this using robotic devices. If a person controls a robotic arm to tickle themselves, they don't feel ticklish. But if there's a delay between their movement and the robotic arm's action, or if the path of the touch is slightly altered, the ticklish sensation returns. The moment the brain can't perfectly predict what's about to happen, sensory attenuation weakens, and the touch feels more intense, more surprising, more ticklish. This also explains why you can't scare yourself by jumping out from behind a door or startle yourself by clapping your hands. Your brain knows it's coming. The prediction removes the element of surprise, and without surprise, there's no emotional or sensory reaction. The same principle applies to why you can't make yourself laugh by telling yourself a joke. The outcome is known, so the brain doesn't treat it as novel or unexpected. Interestingly, people with certain neurological conditions, particularly schizophrenia, sometimes report being able to tickle themselves. This likely relates to disruptions in the brain's prediction systems. When the cerebellum or other regions responsible for sensory prediction aren't functioning typically, self-generated actions might not be properly tagged as self. The brain treats them as external, and the usual filtering doesn't happen. This can also lead to other sensory distortions, like feeling as though one's own movements are being controlled by someone else. The inability to tickle yourself is a small but clear example of how much your brain is constantly doing behind the scenes. It's not just passively receiving information from the world. It's actively predicting, filtering, and shaping your experience of reality. Every sensation you feel has been processed through layers of prediction and comparison. What gets through to your conscious awareness is only what the brain decides is worth paying attention to. Tickling, in this sense, isn't really about the touch itself. It's about the mismatch between expectation and reality. And since you can't surprise yourself, you can't tickle yourself. Your brain is simply too good at knowing what you're about to do. Every second your brain is flooded with information. Sights, sounds, smells, sensations, thoughts. If all of it were stored permanently, your mind would be overwhelmed, cluttered with irrelevant details. So the brain has a system. It filters, sorts, and decides what's worth keeping and what can be discarded. But how does it make that decision? What determines whether a moment becomes a lasting memory or fades within seconds? The process starts in the hippocampus, a seahorse-shaped structure deep in the brain that acts as a gatekeeper for memory. When you experience something, the information first enters short-term or working memory, a temporary holding space that lasts only seconds to minutes. Think of it like a scratch pad. You use it to remember a phone number long enough to dial it, or to hold a thought while you finish a sentence. But unless something else happens, that information disappears. The brain erases it to make room for what's coming next. For information to move from short-term to long-term memory, the hippocampus has to decide it's important. And the biggest factor in that decision is emotion. Emotional experiences get prioritized. This is why you remember your first day of school, a surprising piece of news, or a moment of fear far more vividly than you remember what you ate for lunch 3 days ago. When something emotionally significant happens, the amygdala, the brain's emotion center, becomes active. It sends signals to the hippocampus, essentially tagging the memory as important. Keep this. This emotional tagging isn't arbitrary. From an evolutionary perspective, it makes sense. Memories tied to strong emotions, especially fear or pleasure, often relate to survival or social bonding. If you barely escape danger, remembering that experience could save your life later. If a certain action led to reward, remembering it helps you repeat the behavior. The brain evolved to prioritize what matters for survival and well-being, and emotion is the clearest signal of what matters. But emotion isn't the only factor. Repetition also plays a role. If you encounter the same information multiple times, the brain interprets that repetition as a sign of importance. This is why studying or practicing something over and over eventually moves it into long-term storage. Each repetition strengthens the neural pathways associated with that memory, making it more stable and easier to retrieve. Without repetition, even emotionally neutral information can become permanent if it's reviewed or revisited enough. Attention is another key element. If you're not paying attention when something happens, it's unlikely to be encoded as a memory at all. You've probably had the experience of someone telling you something, and moments later, you realize you didn't actually hear them. The information reached your ears, but your brain wasn't attending to it, so it never made it past the initial sensory stage. Attention directs the brain's resources toward specific information, increasing the likelihood that it will be encoded. The transfer from short-term to long-term memory happens through a process called consolidation. This is when the brain replays and reinforces the memory, often during sleep. When you sleep, particularly during deep sleep and REM stages, the hippocampus communicates with the cortex, transferring memories from temporary storage to more permanent networks distributed throughout the brain. This is why sleep is so critical for learning. Without it, memories don't consolidate properly, and information that seemed clear the night before can be fuzzy or lost by morning. Not all long-term memories are the same. Some are explicit, memories you can consciously recall, like facts, events, or personal experiences. Others are implicit, things you know how to do without thinking, like riding a bike or typing on a keyboard. These implicit memories are stored differently, often in areas like the cerebellum and basal ganglia, and they don't rely as heavily on the hippocampus. Memory is also reconstructive, not reproductive. You don't store experiences like video files. You store pieces, fragments, and when you recall a memory, your brain reconstructs it from those pieces. This is why memories can change over time, influenced by new information, suggestions, or emotions. Each time you remember something, you're essentially recreating it, and that process is vulnerable to distortion. The brain's memory system is efficient, but it's not perfect. It prioritizes what seems important in the moment, but importance is subjective and context-dependent. What feels critical today might not matter tomorrow, and what seems trivial might later prove significant. The system is optimized for survival, not for perfect recall, and that trade-off is why we remember some things vividly and forget others entirely, even when we wish it were the other way around. You dip your hand into ice water, and within seconds it's not just cold. It hurts. A sharp, biting sensation that makes you want to pull away immediately. It's not the same as touching something rough or getting pinched. It's pain, but it's caused by temperature. Why does extreme cold cross the line from sensation into something that genuinely hurts? The answer lies in how your body processes temperature. Your skin is covered with specialized receptors that detect heat and cold. These thermoreceptors are separate from the receptors that detect pressure or touch. When you touch something moderately cold, these receptors send signals to your brain that register as cold, a distinct sensation that's uncomfortable but not painful. But when the temperature drops below a certain threshold, something changes. The cold receptors become overwhelmed, and other pathways get involved. At extreme temperatures, both hot and cold, the signals start activating nociceptors, the sensory neurons responsible for detecting pain. This overlap isn't accidental. It's a protective mechanism. Your body treats extreme temperature as a threat, something that could cause tissue damage, and pain is the alarm system. The brain doesn't just want you to notice the cold. It wants you to react immediately, to remove yourself from the danger before frostbite or other injury occurs. The specific receptor involved in cold pain is called TRPM8, a protein that responds to cooling. Under normal conditions, it sends signals that your brain interprets as a cooling sensation. But when temperatures drop significantly, TRPM8 receptors fire more intensely, and the signal crosses over into pain pathways. There's also another receptor, TRPA1, that activates in response to noxious cold, the kind of cold that's genuinely harmful. When TRPA1 gets involved, the brain interprets the sensation as pain, not just temperature. This is why cold water feels painful almost immediately, while cold air might just feel uncomfortable. Water conducts heat away from your body much faster than air does. When you plunge your hand into ice water, your skin temperature drops rapidly, and the receptors respond to that steep gradient. The faster the temperature change, the more intense the signal, and the more likely it is to be perceived as pain. There's also a phenomenon called paradoxical heat, where extreme cold can actually feel hot. This happens when cold temperatures activate both cold receptors and heat receptors simultaneously, confusing the brain's interpretation. People sometimes describe frostbitten skin as burning, not freezing, because the sensory signals are mixed. The brain is receiving conflicting information, and the result is a sensation that doesn't match the actual temperature. Pain from cold is also influenced by duration. If you keep your hand in cold water, the initial sharp pain often transitions into a deeper, more persistent ache. This is because prolonged cold exposure affects not just the surface receptors, but also the underlying tissues, muscles, and nerves. Blood vessels constrict to preserve core body temperature, reducing blood flow to the extremities. This lack of circulation contributes to the aching sensation and can eventually lead to numbness, as the nerves themselves are affected by the cold. The body's response to cold pain is part of a broader survival system. In the same way that touching a hot stove triggers an instant reflex to pull your hand back, cold pain prompts immediate withdrawal. You don't have to think about it. The signal travels through your spinal cord and triggers a reflex before it even reaches your conscious awareness. By the time you're thinking, "That's cold," your hand is already moving. Interestingly, people have different pain thresholds for cold. Some can tolerate ice baths with minimal discomfort, while others find even moderately cold water intolerable. This variation is partly genetic, related to differences in receptor density and pain pathway sensitivity, and partly psychological, shaped by past experiences and mental conditioning. Cold pain is a reminder that pain isn't just about injury, it's about threat. The body uses pain as a signaling system, a way to communicate urgency. And when it comes to extreme temperatures, the message is clear. This could hurt you, move now. The sensation is unpleasant by design, ensuring that you listen and respond before real damage occurs. Something difficult happens. A loss, a betrayal, a major disappointment. In the immediate aftermath, you might feel numb, shocked, or strangely functional. You go through the motions, handle what needs to be handled. People might even comment on how well you're holding up. But then 2 or 3 days later it hits. The weight of it crashes down, and suddenly you're feeling everything you didn't feel before. This is what some people call the third-day rule, and it's not just coincidence. There's a biological and psychological reason why emotions often peak around 72 hours after an event. The first factor is cortisol, the body's primary stress hormone. When something traumatic or emotionally significant happens, your body immediately floods your system with cortisol. This is part of the acute stress response, the fight or flight system that helps you deal with immediate threats. Cortisol sharpens focus, suppresses non-essential functions, and keeps you alert. In the short term, this is useful. It allows you to function, to make decisions, to get through the crisis without falling apart. But cortisol doesn't stay elevated indefinitely. After the initial spike, it begins to cycle. The body tries to return to baseline, but it doesn't happen smoothly. Cortisol levels can dip and then spike again as your system processes what happened. This cycling often peaks around the second or third day. When cortisol drops after being elevated, you can experience a kind of crash. The numbness wears off, and the emotions that were suppressed by the stress response come flooding in. What felt manageable on day 1 becomes overwhelming on day 3. There's also an element of delayed emotional processing. In the immediate aftermath of a difficult event, your brain is focused on survival and practicality. It's managing logistics, making arrangements, dealing with the situation at hand. The prefrontal cortex, the part of your brain responsible for planning and reasoning, is in control. But once the immediate demands ease, the emotional centers of the brain, particularly the amygdala and the limbic system, start catching up. They begin fully processing what happened, and that processing brings the emotions to the surface. This delay is why people often report feeling fine right after bad news, only to break down days later. The brain compartmentalizes. It holds off on the emotional response until it feels safe to experience it. Once the crisis mode fades and you're no longer in immediate danger or under immediate pressure, the brain allows the emotions to come through. It's a protective mechanism, but it also means the emotional impact is postponed, not avoided. Sleep also plays a role. In the first day or two after a stressful event, sleep is often disrupted. You might not sleep at all, or your sleep might be fragmented and restless. During sleep, especially REM sleep, the brain processes emotions and consolidates memories. When sleep is disrupted, that processing is delayed. By the third day, if sleep starts to normalize, the brain begins working through the emotional content of the experience, and that can bring intense feelings to the surface, sometimes through dreams, sometimes through waking emotional waves. There's also a social and cognitive component. In the first couple of days, people around you might be offering support, checking in, providing distraction. But by day 3, life starts returning to normal for everyone else. The phone calls taper off, people go back to their routines, and you're left alone with your thoughts. The absence of external support can make the emotions feel more intense. You're no longer being held up by others, and the weight of the experience becomes fully your own to carry. The third-day rule isn't universal. Some people feel the full impact immediately. Others take longer. But the pattern is common enough to be recognized, especially in grief, trauma, and major life transitions. It's the point where the shock wears off, the adrenaline fades, and the reality of what happened starts to settle in. Understanding this pattern can be helpful. It reminds you that delayed emotional responses aren't a sign of weakness or that something's wrong with you. It's how the body and brain manage overwhelming experiences. The emotions aren't gone in those first couple of days. They're just waiting, held in reserve until your system is ready to process them. And when they arrive, often around that third day, they arrive with full force. You blink about 15 to 20 times per minute. Each blink lasts around 1/10 of a second. That means over the course of a day, your eyes are closed for roughly 10% of your waking hours. And yet, you never experience the world as a series of interrupted images. You don't see black gaps or feel like the visual world is flickering on and off. Everything appears smooth, continuous, uninterrupted. How does the brain create this seamless experience when your eyes are constantly closing? The answer lies in a process called saccadic masking, though it applies to blinks as well. Saccadic masking is the brain's way of suppressing visual input during rapid eye movements, and it extends to blinking. When you blink, your eyelids briefly block light from reaching your retina, but the brain doesn't register this as darkness. Instead, it actively suppresses the signal. It essentially tells itself, ignore this, it's not important. The visual cortex, the part of the brain that processes sight, reduces its activity during the blink, preventing you from perceiving the interruption. But suppression alone doesn't fully explain the continuity. The brain also uses something called visual memory buffers. Before you blink, your brain takes a snapshot of what you're seeing. It holds that image in a very short-term visual memory, just long enough to bridge the gap created by the blink. When your eyes reopen, the brain compares the new image to the stored one. If they match closely enough, the brain treats the experience as continuous. You're not consciously aware of this comparison. It happens automatically, in milliseconds, seamlessly integrating the before and after into a single, uninterrupted stream of perception. This process is similar to what happens during saccades, the rapid eye movements your eyes make when scanning a scene. Your eyes don't move smoothly across the world. They jump from point to point, several times per second. During each jump, your vision would blur if your brain didn't suppress it. So it does. Saccadic masking blocks the blurry image, and the brain fills in the gaps using the visual information from before and after the movement. The result is a stable, continuous perception, even though the input is fragmented. The brain is also very good at prediction. It anticipates what the visual scene should look like when your eyes reopen, based on the context and recent history. If you're looking at a stationary object, the brain expects it to still be there after the blink. If you're watching something move, the brain predicts where it will be by the time your eyes open again. These predictions help maintain the sense of continuity, even when the actual visual input is briefly absent. This predictive filling-in is so effective that you usually don't notice small changes that occur during a blink. This phenomenon is exploited in magic and film editing. Magicians sometimes make moves during a spectator's blink, knowing the brain will smooth over the transition. Film editors use cuts during moments that mimic natural breaks in attention, like blinks, to create seamless scene changes without the viewer noticing the disruption. The brain's ability to mask blinks is also why you don't see your own blinks when looking in a mirror. You might think you'd catch a glimpse of your eyelids closing, but you don't. The brain suppresses the blink in real time, so even your reflection appears to have uninterrupted vision. However, if you record yourself and watch it back, you'll see the blinks clearly. The suppression only works in the moment, not on playback. There's also a temporal aspect to this. The brain doesn't just fill in space, it fills in time. It creates the illusion that time flows smoothly, even though your perception is actually a patchwork of snapshots, predictions, and brief interruptions. This is part of a larger truth about perception. What you experience as reality is a constructed model, built by your brain from incomplete and intermittent data. The seamlessness is an illusion, but it's a necessary one. If you were consciously aware of every blink, every saccade, every gap in visual input, your experience of the world would be chaotic and disorienting. Instead, the brain does the work behind the scenes, editing out the interruptions, smoothing over the gaps, and presenting you with a version of reality that feels continuous and stable. You see the world not as it actually arrives at your eyes, but as your brain decides it should be perceived. You step outside on a sunny day, and within seconds you sneeze. It's not allergies, not dust, just the sudden exposure to bright light. Or maybe you've never experienced this, and it sounds completely strange. If you're in the first group, you have something called the photic sneeze reflex, and you're not alone. About 18 to 35% of the population has it, though most people don't know there's a name for it. The photic sneeze reflex, sometimes called ACHOO syndrome, autosomal dominant compelling helio-ophthalmic outburst, a playful backronym, is a genetic trait. If one of your parents has it, there's a good chance you do too. It's inherited in an autosomal dominant pattern, meaning you only need one copy of the gene variant to express the trait. But despite being relatively common and documented for centuries, scientists still don't fully understand why it happens. The most widely accepted explanation involves crossed wires in the nervous system. Sneezing is controlled by the trigeminal nerve, a major nerve in your face that handles sensation and certain reflexes. When something irritates your nasal passages, dust, pollen, strong smells, the trigeminal nerve sends a signal to the brainstem, which triggers the sneeze reflex. But the optic nerve, which carries visual information from your eyes to your brain, runs very close to the trigeminal nerve. And in some people, these two systems seem to interfere with each other. When bright light suddenly hits your eyes, the optic nerve fires intensely to transmit that information to the brain. In people with the photic sneeze reflex, this strong signal from the optic nerve appears to activate the nearby trigeminal nerve as well. The brain misinterprets the signal, treating the burst of light as if it were an irritant in the nose, and triggers a sneeze. It's a case of neural crosstalk, where one system's activity spills over into another. Another theory involves the pupillary light reflex, the automatic constriction of your pupils in response to bright light. This reflex is also mediated by nerves connected to the brainstem, and it's possible that in some individuals, the activation of this reflex inadvertently stimulates the sneeze center as well. The exact mechanism is still debated, but the common thread is that bright light triggers a response in a system that shouldn't normally be involved in vision. The photic sneeze reflex is typically triggered by sudden changes in light intensity, not just any bright light. Walking from a dark room into sunlight, looking directly at a light bulb, or even thinking about bright light in some cases can set it off. The sneeze usually happens within seconds of the exposure and often occurs in clusters, 2 or 3 sneezes in quick succession. For most people, the reflex is harmless, just a quirky, mildly annoying trait, but it can be problematic in certain situations. Pilots, for example, have reported concerns about sneezing during critical moments like landing when transitioning from clouds into bright sunlight. Similarly, drivers emerging from tunnels into daylight might experience a sudden sneeze, which, while brief, can be distracting. There's also a cultural and historical element to this reflex. Ancient Greek philosophers, including Aristotle, wrote about sneezing in response to sunlight, though their explanations were, unsurprisingly, off the mark. Aristotle thought the heat of the sun caused the nose to sweat, triggering a sneeze. We now know it's neural, not thermal, but the observation itself was accurate. Interestingly, not everyone with a genetic predisposition experiences the reflex every time they're exposed to bright light. It can be inconsistent, affected by factors like fatigue, nasal congestion, or even mood. Some people only notice it in certain contexts or during certain times of the year. The photic sneeze reflex is a reminder that the human body is full of quirks, small variations in wiring that don't necessarily serve a purpose but aren't harmful either. It's not an adaptation. It's not beneficial. It's just a side effect of how closely packed and interconnected our neural systems are. And for the significant minority of people who have it, bright light will always come with the risk of an unexpected sneeze. Nails on a chalkboard, a fork scraping a plate, a baby crying, a dog whining. Certain sounds don't just annoy you, they make your skin crawl, your shoulders tense. You feel an almost physical urge to cover your ears or leave the room. The reaction is immediate, visceral, and hard to control. Why do some sounds provoke such an intense response? The answer starts with frequency. The human ear can detect sounds across a wide range, from about 20 Hz to 20,000 Hz, but not all frequencies are processed equally. The range between 2,000 and 5,000 Hz is where the ear is most sensitive, and it's also where many of the most unbearable sounds fall. This isn't random. This frequency range is where human voices, especially the cries of infants, are most prominent. Evolutionarily, it makes sense that we'd be highly attuned to these sounds. A baby's cry needed to capture attention immediately, triggering a caregiving response. But that same sensitivity means we're also vulnerable to other sounds in this range, even when they're not distress signals. When you hear a sound in this frequency range, especially if it's harsh or irregular, your auditory cortex processes it, but it doesn't stop there. The signal also reaches the amygdala, the brain's emotional center. The amygdala is responsible for processing threats, and certain sounds, particularly those that are sharp, loud, or high-pitched, are flagged as potentially dangerous. This triggers a stress response. Your body tenses. Your heart rate might increase. You feel discomfort, sometimes even pain, even though the sound itself isn't causing physical harm. Research has shown that sounds like nails on a chalkboard or metal scraping metal activate the amygdala more intensely than neutral sounds. Brain scans reveal heightened activity in regions associated with pain and aversion. The sound isn't just unpleasant, it's processed as a threat, and your body reacts accordingly. This is why some people describe the experience as painful, even though there's no physical injury. The brain is creating a pain-like response based on the auditory input. There's also an element of unpredictability. Sounds that are irregular, sudden, or jarring are harder for the brain to predict and therefore harder to tune out. Your auditory system is constantly working to filter irrelevant noise, focusing on what's important. But when a sound is erratic, the brain can't filter it effectively. It demands attention, and that constant alertness is exhausting and stressful. This is why repetitive but irregular sounds, like dripping water or a dog barking intermittently, can be so grating over time. Misophonia, a condition where specific sounds trigger intense emotional reactions, takes this to an extreme. People with misophonia might feel rage, panic, or disgust in response to sounds like chewing, breathing, or tapping. These are often sounds made by other people, and the reaction is disproportionate to the actual volume or intensity of the sound. The exact cause of misophonia isn't fully understood, but it's thought to involve heightened connectivity between the auditory cortex and the limbic system, the brain's emotional processing network. The sound isn't just heard, it's felt, emotionally and sometimes physically. There's also a learned component. If you've had a negative experience associated with a particular sound, your brain can form a strong aversion to it. This is a form of classical conditioning. The sound becomes linked to the negative emotion, and every time you hear it afterward, the reaction is triggered automatically. This is why some people can't stand the sound of a dentist's drill or a smoke alarm, even in non-threatening contexts. The sound itself has become a conditioned trigger. Cultural factors play a role too. What's considered an unbearable sound can vary. Some cultures find certain vocal tones or musical intervals grating while others don't. But there are commonalities. Across cultures, sounds associated with distress, danger, or illness, crying, screaming, gagging, tend to provoke strong negative reactions. These are universal signals, and the brain is wired to respond to them. The physical discomfort you feel from certain sounds is real. It's not just sensitivity or preference. It's your brain and body reacting to what they perceive as a threat or a demand for attention. And because the response is largely involuntary, controlled by ancient, automatic systems, it's very hard to simply get over it or ignore the sound. The best you can do is remove yourself. Use sound protection, or, in some cases, work with exposure therapy to reduce the intensity of the reaction over time. You cut your finger. Blood flows, then clots. Over the next days and weeks, the wound closes, skin reforms, and eventually there's barely a trace. But here's what's remarkable. The skin doesn't just grow back randomly. It reconstructs itself in the same pattern, the same layers, the same structure it had before. How does your body know exactly how to rebuild what was lost? The answer lies in cellular memory and local tissue architecture. Every cell in your body carries the complete genetic blueprint, your DNA, but not every gene is active in every cell. Skin cells know they're skin cells because specific genes are turned on and others are turned off. This identity isn't just about what the cell is, it's also about where the cell is. Cells know their position relative to their neighbors, and they use that information to guide healing. When you get a cut, the injury disrupts this organized structure. Cells at the edge of the wound immediately sense the damage. They detect the absence of their usual neighbors and the sudden exposure to the external environment. This triggers a cascade of signals, chemical messages that tell nearby cells to start the repair process. The first responders are platelets, which form a clot to stop the bleeding. Then immune cells arrive to clear out debris and fight infection. But the real reconstruction work begins with the cells that remain in the surrounding tissue. These surviving cells contain what's called positional information. They know where they are in the tissue's architecture, and they use chemical gradients to communicate this information. Growth factors, proteins that promote cell division and movement, are released in specific patterns. Cells on one side of the wound produce slightly different concentrations of these factors than cells on the other side, creating a gradient. This gradient acts like a map, guiding new cells to grow in the right direction and stop at the right point. Fibroblasts, the cells responsible for producing collagen and other structural proteins, migrate into the wound area. They don't just dump collagen randomly. They align it according to the tension and direction of the surrounding tissue. If the original skin had collagen fibers running in a particular pattern, the fibroblasts attempt to replicate that pattern. They're guided by mechanical cues, the pull and stretch of the tissue, and by chemical signals from neighboring cells. Keratinocytes, the primary cells of the outer skin layer, also play a critical role. They begin at the wound's edge and slowly migrate inward, covering the exposed area. As they move, they're constantly communicating with each other and with the underlying tissue. They know when to stop dividing and moving based on contact inhibition, a process where cells stop growing once they touch other cells and sense that the gap is closed. What's fascinating is that cells don't need instructions from the brain or any central control system. The information is local, stored in the tissue itself. Each cell responds to its immediate environment, the chemicals around it, the physical forces acting on it, the presence or absence of other cells. This decentralized system allows the body to repair damage efficiently, even in areas far from the central nervous system. However, the healing isn't always perfect. If the wound is large or deep, or if healing is interrupted by infection or movement, the body prioritizes speed over precision. Scar tissue forms, which is essentially a quick patch job. Scar tissue is made of the same collagen as regular skin, but it's organized differently. Instead of the basket weave pattern of healthy skin, scar collagen runs in parallel lines. It's strong but less flexible, and it doesn't contain hair follicles, sweat glands, or the same pigmentation as the surrounding skin. The body's ability to heal in the original pattern also depends on the presence of stem cells in the tissue. These are undifferentiated cells that can become whatever type of cell is needed. In skin, stem cells reside in the deeper layers and in hair follicles. When damage occurs, these stem cells activate, divide, and differentiate into the specific cell types needed for repair. As long as these stem cells are present and functioning, the body can reconstruct tissue with remarkable fidelity to the original. There are limits. Some tissues, like the heart and central nervous system, have very limited regenerative capacity. When a heart attack damages heart muscle, the body can't fully replace the lost cells. Instead, it forms scar tissue, which doesn't contract like healthy muscle. This is why understanding tissue regeneration is a major focus in medical research. Scientists are trying to figure out how to enhance or reactivate the body's natural repair mechanisms, potentially using growth factors, stem cells, or even genetic modifications. The body's ability to heal in precise patterns is a testament to the sophistication of cellular communication and organization. It's not magic, and it's not centrally controlled. It's millions of cells, each following local rules, each responding to their neighbors, collectively recreating the structure that was lost. The blueprint isn't stored in one place. It's distributed throughout the tissue, held in the relationships between cells, the gradients of chemical signals, and the mechanical properties of the surrounding environment. You're sitting quietly and suddenly you feel it, a vibration in your pocket. You reach for your phone, certain that a notification just came through. But when you check, there's nothing. No call, no text, no alert. The phone is completely still. You felt it vibrate, you're sure of it, but it didn't. This experience is so common it has a name, phantom vibration syndrome, and it reveals something interesting about how your brain processes sensory information. The phenomenon starts with sensory adaptation. Your brain is constantly filtering the flood of sensory input coming from your body. If it paid attention to every sensation, the feeling of your clothes, the pressure of sitting, the subtle movements of your muscles, you'd be overwhelmed. So the brain learns to tune out constant, unchanging stimuli. It only alerts you to changes, things that might be important or require a response. But here's the issue. When you carry your phone in the same place every day, and it vibrates multiple times throughout that day, your brain starts to form an expectation. It creates a pattern. Vibration in pocket equals notification. Over time, this association becomes so strong that your brain begins to anticipate it. And in moments of ambiguity, when there's any slight sensation in that area, a muscle twitch, the brush of fabric, even the shift of weight as you move, your brain interprets it as the familiar vibration pattern. This is pattern-seeking behavior, and your brain is exceptionally good at it. It's the same system that lets you recognize faces in clouds or hear words in random noise. The brain is designed to find meaning, even in incomplete or ambiguous data. When it encounters a sensation that's even remotely similar to a phone vibration, it fills in the gaps, jumping to the conclusion that matches the learned pattern. There's also a component of hypervigilance. If you're in a state where you're expecting or hopping for a message, maybe you're waiting for important news, or you're anxious about missing something, your brain's threshold for detecting the vibration drops. It becomes oversensitive, more likely to false alarm. This is why phantom vibrations tend to increase during periods of stress or when you're anticipating communication. Your brain is on high alert, and it's interpreting even weak or irrelevant signals as potential notifications. The sensation is real in the sense that you genuinely feel something. It's not imagined. Your somatosensory cortex, the part of the brain that processes touch, is actually activating. But the trigger isn't the phone. It's a misinterpretation of another stimulus. Your brain is essentially creating the sensation internally, based on expectation and pattern recognition, rather than responding to an external vibration. Studies have shown that phantom vibrations are more common in people who use their phones frequently and who keep them in the same location consistently. The brain learns the specific pattern of that phone's vibration and the specific location where it occurs. The more consistent the pattern, the stronger the association, and the more likely the phantom sensation becomes. Interestingly, this isn't unique to phones. Before smartphones, people reported similar phenomena with pagers, and it's not limited to vibration. Some people experience phantom ringing, hearing their ringtone when the phone isn't actually ringing. The mechanism is the same. The brain has learned a pattern and is now over-applying it, interpreting ambiguous auditory input as the familiar sound. The phenomenon is generally harmless, just a minor annoyance, but it does highlight how much your perception is shaped by expectation and learned associations. You don't experience reality directly. You experience your brain's interpretation of reality, filtered through patterns, predictions, and priorities. And when those predictions are strong enough, they can create sensations that feel entirely real, even when the external trigger doesn't exist. If phantom vibrations bother you, the solution is to break the pattern. Change where you carry your phone, turn off vibration entirely, or reduce how often you check it. The less consistent the association, the weaker the phantom sensation becomes. Your brain will eventually unlearn the pattern, and the false alarms will fade. You're drifting off to sleep, your body relaxing, your mind starting to fade. Then suddenly you jerk awake, your heart racing with the unmistakable sensation that you were falling. Your muscles tense all at once, your arms might flail, and for a brief, disorienting moment, you're convinced you were about to hit the ground. But you weren't falling. You were lying in bed the entire time. This experience is called a hypnic jerk, and it's one of the strangest sensations the body produces during the transition to sleep. Hypnic jerks, also called sleep starts, happen to most people at least occasionally. For some, they're a regular occurrence. The sensation can vary. Sometimes it's a full-body jolt. Sometimes it's just a twitch in one limb. Often, it's accompanied by a vivid, brief sensation of falling, tripping, or missing a step. But despite how startling they feel, hypnic jerks are completely normal, a harmless quirk of the nervous system as it shifts from wakefulness to sleep. The leading explanation involves the way your muscles relax as you fall asleep. During wakefulness, your muscles maintain a baseline level of tension, enough to keep you upright, responsive, and ready to move. But as you transition into sleep, particularly into the first stage of non-REM sleep, your muscles begin to relax completely. This relaxation happens gradually, but it's not always smooth. The brainstem, which controls many automatic functions, including muscle tone, sometimes misinterprets this sudden relaxation. One theory suggests that the brainstem's reticular activating system, which helps regulate wakefulness and muscle activity, occasionally misreads the muscle relaxation as a sign of physical instability. In other words, as your muscles go limp, your brainstem might perceive this as falling or losing balance, even though you're lying down. In response, it sends out a quick, corrective signal, a burst of motor activity designed to catch yourself. The result is the sudden jerk, the tensing of muscles, and the sensation of falling. This is sometimes described as the brain's safety check. As you lose consciousness, the systems that keep you alert and responsive start to shut down. But they don't all shut down at once, and there can be moments of conflict between systems that are asleep and systems that are still partially awake. The hypnic jerk might be a remnant of an old survival mechanism, a reflex that kept our ancestors from falling out of trees or off cliffs while sleeping in precarious positions. Even though modern humans sleep in safe, flat beds, the reflex remains. There's also a connection to the hypnagogic state, the transitional phase between wakefulness and sleep. During this phase, your brain is in a strange in-between place. You might experience vivid imagery, hear sounds that aren't there, or feel sensations that don't correspond to reality. The feeling of falling is one of these hypnagogic hallucinations. Your brain is starting to dream, but you're not fully asleep yet. So the dream content, a sensation of movement or instability, gets interpreted as real, triggering the physical jerk. Certain factors make hypnic jerks more likely. Stress, anxiety, and caffeine can all increase their frequency. When you're stressed, your nervous system is more excitable, more likely to overreact to small changes. Caffeine, even consumed hours before bed, can keep your nervous system on edge, making the transition to sleep less smooth. Physical exhaustion can also play a role. If your body is deeply fatigued, the shift from wakefulness to sleep can be more abrupt, increasing the chance of a misinterpretation by the brainstem. Irregular sleep schedules contribute as well. If you're going to bed at different times or not getting enough sleep overall, your nervous system doesn't have a consistent pattern to follow. The transition to sleep becomes less predictable, and the hypnic jerk is more likely to occur. The sensation is brief, usually lasting only a second or two, but it can be jarring enough to fully wake you up. Some people experience a brief moment of confusion or fear, especially if the falling sensation was vivid. But once you realize you're in bed and safe, the feeling passes. The hypnic jerk doesn't indicate any underlying health problem. It's not a seizure, and it's not a sign of a sleep disorder. It's just a small glitch in the transition between waking and sleeping, a moment where your brain and body aren't quite in sync. If hypnic jerks are frequent enough to disrupt your sleep, improving sleep hygiene can help. Going to bed at the same time each night, reducing caffeine and stress, and creating a calming pre-sleep routine can all make the transition smoother and reduce the frequency of these jolts. But for most people, hypnic jerks are just an occasional, strange reminder of how complex and imperfect the process of falling asleep really is. Tears are tears, right? They're just water and salt produced by glands in your eyes. But it turns out not all tears are the same. The tears you cry when you chop an onion are chemically different from the tears you cry during a sad movie or a moment of grief. Your body produces distinct types of tears depending on why you're crying, and the differences aren't just symbolic. They're measurable, biological, and they reveal something fascinating about the connection between emotion and physical response. There are three main types of tears: basal, reflex, and emotional. Basal tears are the ones your eyes produce constantly, a thin film that keeps your eyes lubricated, protects them from dust and debris, and provides nutrients to the cornea. You don't notice them unless something goes wrong and your eyes feel dry. Reflex tears are the body's response to irritation, smoke, wind, a strong smell like onions, or a foreign object in the eye. These tears are produced quickly and in large volume, designed to flush out whatever is causing the irritation. Emotional tears, the ones triggered by feelings, are different. They come from the same lacrimal glands, located above and to the side of each eye, but they're activated by a different pathway. While reflex tears are triggered by sensory nerves responding to physical irritation, emotional tears are triggered by the limbic system, the part of the brain that processes emotions. When you feel sadness, grief, overwhelming joy, or even intense frustration, signals from the limbic system travel to the lacrimal glands, activating them to produce tears. What makes emotional tears unique is their chemical composition. All tears contain water, salts, oils, and mucus, but emotional tears also contain higher levels of certain proteins and hormones. One of these is prolactin, a hormone associated with stress and emotional regulation. Another is leucin and enkephalin, a natural painkiller produced by the brain. Emotional tears also contain higher concentrations of manganese and potassium, both of which are linked to stress regulation. Some researchers believe that emotional crying serves a function beyond communication. The act of crying might actually help regulate your emotional and physiological state. By releasing stress hormones and other chemicals through tears, the body could be physically expelling some of the byproducts of emotional distress. This would explain why people often report feeling better after a good cry, a sense of relief or catharsis. It's not just psychological. It could be biochemical, the body literally releasing tension through tears. The pathway for emotional tears also explains why crying is so closely tied to specific emotions. The limbic system, which includes the amygdala and hippocampus, is deeply involved in processing emotional experiences, especially those tied to memory, loss, or social bonding. When these areas are activated intensely, they can trigger the tear response. This is why you might cry at a funeral, during a heartfelt conversation, or while watching a movie that taps into deep emotions. The tears aren't a conscious choice. They're an automatic response, driven by the emotional intensity of the moment. Interestingly, emotional tears are uniquely human. While other animals produce basal and reflex tears, there's no clear evidence that any other species cries in response to emotion. Some researchers suggest that emotional crying evolved as a social signal, a way to communicate vulnerability, distress, or need for support without words. Tears are highly visible, especially on the face, and they're difficult to fake convincingly. They signal genuine emotion, which can prompt empathy and caregiving behavior from others. There's also a developmental aspect. Bobbies cry reflexively when they're uncomfortable, hungry, or in pain. But as humans develop, crying becomes more tied to emotional and social contexts. Adults cry far less frequently than children, but when they do, it's almost always in response to emotional rather than physical stimuli. The shift reflects the maturation of the limbic system and the increasing complexity of emotional life. Not everyone cries easily, and that's not necessarily a sign of emotional suppression or dysfunction. Tear production and the threshold for emotional crying vary widely between individuals, influenced by genetics, hormones, culture, and personality. Some people cry at the slightest emotional trigger. Others rarely cry, even in situations that would move most people to tears. Both are normal variations. The chemical differences in emotional tears suggest that crying is more than just an outward expression of feeling. It's a physiological process, integrated into the body's stress response and emotional regulation systems. When you cry, your body isn't just reacting. It's actively processing, releasing, and attempting to restore balance. The tears themselves are part of that process, carrying away more than just moisture. You catch a whiff of something, maybe a particular perfume, fresh-cut grass, or the smell of rain on pavement, and suddenly you're transported. Not just reminded, but pulled into a vivid memory. You can see the place, feel the emotions, remember details you hadn't thought about in years. It happens instantly, without effort, and the memory feels more real than if you tried to recall it deliberately. Why do smells have this unique power to unlock the past? The answer lies in the anatomy of the olfactory system, the way your brain processes smell. Unlike your other senses, which send information through the thalamus, a kind of relay station that organizes and distributes sensory data, smell takes a direct route. When you inhale a scent, odor molecules bind to receptors in your nose, and those receptors send signals straight to the olfactory bulb, a structure at the base of the brain. From there, the information travels immediately to two key areas: the amygdala, which processes emotions, and the hippocampus, which handles memory formation and retrieval. This direct connection is what makes smell so intimately tied to memory and emotion. There's no intermediate processing, no filtering. The scent reaches the emotional and memory centers of your brain almost instantly, and because these areas are so closely linked, the memory that gets triggered often comes with the full emotional weight of the original experience. You don't just remember the event, you feel it again. This is why smell-triggered memories, sometimes called Proustian memories after the French writer Marcel Proust, who famously described the experience in his novel, tend to be so vivid and emotionally charged. Other senses can trigger memories too. A song can remind you of a specific time in your life. A photograph can bring back a moment. But those memories tend to feel more detached, more like you're observing them from the outside. Smell-triggered memories feel immersive, as if you've stepped back into the moment itself. The hippocampus is particularly important here. It's responsible for encoding new memories and for linking sensory information to context. When you experience something for the first time, your hippocampus creates associations between the event, the emotions you felt, and the sensory details, sights, sounds, and smells. Later, when you encounter one of those sensory cues again, the hippocampus uses it to retrieve the entire memory. But because smell has such a direct pathway to the hippocampus, and because it's processed alongside emotion in the amygdala, scent-based cues are especially effective at bringing back not just the facts of a memory, but the feeling of it. There's also a phenomenon called odor-evoked autobiographical memory. Research shows that memories triggered by smell tend to be older, often from childhood or adolescence. This might be because the olfactory system is fully developed early in life, and the strong emotional experiences of youth are encoded deeply. Once those associations are formed, they remain stable for decades. A smell that was present during a significant moment in your childhood can still trigger that memory 30 or 40 years later, even if you haven't encountered the scent in all that time. The specificity of smell also plays a role. There are hundreds of different odor receptors in your nose, each tuned to detect specific molecular structures. This allows you to distinguish thousands of different smells. Each scent is a unique combination of activated receptors, creating a distinct neural signature. When that exact combination is encountered again, it activates the same pattern in your brain, pulling up the associated memory with remarkable precision. This is why a smell can bring back a memory that you couldn't access through any other means. You might not be able to remember your grandmother's house if you just sit and try to recall it. But if you smell the same brand of soap she used, or the specific scent of her kitchen, the memory can come flooding back, complete with visual details, sounds, and emotions that were otherwise inaccessible. Interestingly, the connection between smell and memory can also be manipulated. Some people use scent intentionally as a memory aid, associating a particular smell with studying material, then exposing themselves to that same smell during a test. The scent acts as a retrieval cue, helping to access the information more easily. This technique leverages the same neural pathways that create spontaneous scent memories. The power of smell to trigger memory is a reminder of how deeply our senses are woven into our emotional and cognitive lives. Memories aren't stored as isolated facts. They're embedded in a web of sensory and emotional associations. And because smell connects so directly to the brain's memory and emotion centers, it has the unique ability to bypass conscious thought and pull you straight back into the past, into moments you thought you'd forgotten. You hear someone speak for the first time and something about their voice pulls you in. It's not what they're saying, it's how they sound. The tone, the pitch, the rhythm. Some voices feel warm, trustworthy, comforting. Others sound harsh, grating, or cold. You form an impression almost instantly, often before the person has finished their first sentence. Why do certain voices appeal to us while others don't? The answer starts with fundamental frequency, the baseline pitch of someone's voice. This is largely determined by the size and shape of the vocal cords, which are influenced by sex hormones, particularly testosterone. In general, people are drawn to voices that signal biological maturity and health. For women, this often means a preference for deeper male voices, which indicate higher testosterone levels. Deeper voices in men are associated with physical strength, dominance, and reproductive fitness, traits that were likely advantageous in ancestral environments. But the preference isn't absolute. Context matters. In situations where cooperation and trustworthiness are valued, slightly higher-pitched male voices can be more appealing because they're perceived as less threatening, more approachable. Similarly, men tend to prefer women's voices that are higher pitched and more melodic, which are associated with youth and fertility. But again, this isn't universal. Voices that are too high can sound childlike or insincere, and moderate pitch often wins out over extremes. Beyond pitch, vocal tone carries a wealth of social information. Tone conveys emotion, intention, and personality. A voice can sound confident or uncertain, kind or aggressive, calm or anxious. You pick up on these cues automatically, often within milliseconds. This is because your brain is constantly analyzing not just the words being spoken, but the prosody, the musical quality of speech that includes rhythm, stress, and intonation. Prosody tells you how to interpret the words. The same sentence can mean completely different things depending on tone. There's also a phenomenon called vocal attractiveness, which goes beyond pitch. Attractive voices tend to be clear, resonant, and well-modulated. They have a pleasant timbre, the unique quality that distinguishes one voice from another, even at the same pitch. Timbre is influenced by the shape of the vocal tract, the throat, mouth, and nasal passages, and by how precisely someone articulates their words. Voices that are breathy, nasal, or strained are generally less attractive because they signal potential health issues or vocal strain. Interestingly, people also tend to prefer voices that are similar to their own or to the voices they grew up hearing. This is called the familiarity effect. If you grew up in a region with a particular accent or vocal pattern, you're more likely to find that pattern comforting and trustworthy, even if you've since moved away. Your brain associates the familiar vocal qualities with safety and social belonging. There's an evolutionary layer to this as well. Voice can signal health in ways that aren't immediately obvious. Chronic illness, respiratory issues, or hormonal imbalances can all affect voice quality. A strong, clear voice suggests a healthy respiratory system and stable hormone levels. Conversely, a weak or strained voice might indicate underlying health problems. Your brain picks up on these subtle cues, using them to make rapid assessments about a person's fitness and reliability. Vocal attractiveness also changes with context. In professional settings, people tend to prefer voices that sound competent and authoritative. Lower-pitched voices are often rated as more credible and persuasive, which is why many politicians and public speakers intentionally lower their pitch. But in intimate or social settings, warmth and expressiveness become more important. A voice that's too deep or too monotone can feel distant or unapproachable. There's also something called vocal fry, a low, creaky sound that happens when the vocal cords are relaxed and vibrating slowly. It's become more common, particularly among younger women, and it's polarizing. Some find it trendy or relatable. Others find it annoying or unprofessional. The reaction often depends on age, cultural background, and personal associations with the sound. Mirroring plays a role too. When people like each other, they unconsciously start to match vocal patterns, speaking at similar speeds, using similar pitch ranges, even adopting each other's speech rhythms. This is a form of social bonding, a way of signaling rapport and connection. When you're attracted to someone, you're more likely to mirror their voice, and when someone mirrors yours, you're more likely to feel drawn to them. The voice is also tied to memory and emotion. If someone's voice reminds you of a person you loved or trusted, you might feel an immediate positive response. Conversely, if it reminds you of someone who hurt you, the reaction can be negative, even if the new person has done nothing wrong. Your brain is constantly making these associations, often below the level of conscious awareness. Voice preferences aren't just about attraction in a romantic sense. They influence who you trust, who you want to work with, who you find credible, and who you avoid. Your response to someone's voice can shape the entire trajectory of a relationship, all within the first few seconds of hearing them speak. It's a powerful, immediate form of communication, one that operates on both conscious and unconscious levels, shaping your social world in ways you rarely stop to consider. Your body temperature stays remarkably stable, hovering around 98.6 degrees Fahrenheit or 37 degrees Celsius, day after day, regardless of whether you're in a cold room or a hot one, whether you're resting or exercising. This isn't luck or coincidence. It's the result of a highly sophisticated regulatory system that constantly monitors and adjusts your internal temperature to keep it within a narrow, optimal range. But how does the body do this with such precision? The control center is the hypothalamus, a small region at the base of your brain that acts as your body's thermostat. The hypothalamus receives constant input from thermoreceptors, specialized sensors located throughout your body, in your skin, your organs, and even in the hypothalamus itself. These receptors detect changes in temperature and send that information back to the hypothalamus, which compares the current temperature to the set point, the ideal temperature your body is trying to maintain. When the hypothalamus detects that your body is too warm, it triggers cooling mechanisms. The most important of these is vasodilation, the widening of blood vessels near the surface of your skin. When blood vessels dilate, more blood flows close to the skin's surface, where heat can radiate out into the environment. This is why your skin looks flushed when you're hot. The increased blood flow brings more warmth to the surface, allowing it to dissipate. At the same time, your sweat glands activate. Sweat is mostly water, and when it evaporates from your skin, it carries heat away with it, cooling you down. When the hypothalamus detects that you're too cold, it does the opposite. It triggers vasoconstriction, narrowing the blood vessels near your skin to reduce blood flow to the surface. This keeps more heat trapped in your core, preserving warmth where it's most needed. You also start shivering, rapid, involuntary muscle contractions that generate heat as a byproduct. Shivering isn't efficient. It burns energy quickly, but it's an emergency response designed to warm you up fast. Beyond shivering, your body can also increase metabolic heat production, burning more calories to generate warmth even when you're not moving. The precision of this system is remarkable. Your body can detect temperature changes as small as a fraction of a degree and respond within seconds. If you step outside into the cold, your blood vessels start constricting before you even feel uncomfortable. If you start exercising, your body anticipates the heat you're about to generate and begins activating cooling mechanisms in advance. But the set point isn't perfectly fixed at 98.6 degrees. It fluctuates slightly throughout the day, following your circadian rhythm. Body temperature is typically lowest in the early morning, around 4 or 5 a.m., and highest in the late afternoon or early evening. This variation is normal, usually about a degree or so, and it's tied to your body's internal clock. Your metabolism slows during sleep, producing less heat, and ramps up during waking hours when you're more active. The set point can also shift in response to certain conditions. When you have an infection, your immune system releases chemicals called pyrogens, which travel to the hypothalamus and raise the set point. This is what causes a fever. The hypothalamus now thinks the body should be warmer, so it triggers heat-generating responses. Shivering, vasoconstriction, the feeling of being cold even though your actual temperature is elevated. The fever isn't the infection itself. It's the body's intentional response, raising the temperature to create a less hospitable environment for pathogens and to enhance immune function. Hormones also influence temperature regulation. Thyroid hormones, for example, increase metabolic rate, which generates more heat. People with hyperthyroidism and overactive thyroid often feel hot and sweat excessively. Conversely, people with hypothyroidism and underactive thyroid tend to feel cold because their metabolism is slower and generates less heat. Women also experience temperature fluctuations related to the menstrual cycle, with body temperature rising slightly after ovulation due to increased progesterone. There are limits to what the body can handle. If your core temperature drops too low, below about 95 degrees Fahrenheit, hypothermia sets in. The body's systems begin to slow down. Shivering stops because the muscles are too cold to function, and without intervention, organ failure and death can follow. On the other end, if your temperature rises above about 104 degrees, hyperthermia becomes dangerous. Proteins in your body begin to denature, losing their structure and function. The brain is particularly vulnerable to heat, and prolonged high temperatures can cause seizures, confusion, and permanent damage. The body's ability to maintain a stable internal temperature is called homeostasis, and temperature regulation is one of the most critical aspects of it. Almost every biochemical reaction in your body is temperature dependent. Enzymes, the proteins that facilitate these reactions, work best within a narrow temperature range. Even a few degrees of variation can slow them down or stop them entirely. This is why fever, while uncomfortable, is usually kept in check by the body. A slight increase can help fight infection, but too much becomes dangerous. The hypothalamus doesn't work alone. It coordinates with the autonomic nervous system, the part of your nervous system that controls involuntary functions like heart rate, digestion, and breathing. When you need to cool down or warm up, the hypothalamus sends signals through the autonomic nervous system to activate the appropriate responses. Sweating, shivering, changes in blood flow. All of this happens automatically, without conscious thought, allowing your body to maintain its precise internal balance even as the external environment constantly changes. You're sitting alone in a room focused on a task and suddenly you feel it. A prickling sensation at the back of your neck, a shift in awareness. You feel like someone is watching you. You turn around and sometimes someone is there. Other times the room is empty. Either way, the feeling was real. Why does this happen? Why do we sometimes sense another person's gaze, even when we can't see them? The phenomenon is often attributed to peripheral vision. the outer edges of your visual field that detect movement and shapes even when you're not looking directly at them. Your peripheral vision is less detailed than your central vision, but it's far more sensitive to motion and changes in light. This makes evolutionary sense. For most of human history, threats came from the sides, predators, rival groups, environmental dangers. Your peripheral vision evolved to detect these threats quickly, even when your attention was focused elsewhere. When someone enters your peripheral field, even if you don't consciously register their presence, your brain does. It picks up on the movement, the change in the environment, and sends a subtle alert to your conscious awareness. You don't see the person directly, but your brain knows something has changed, and it interprets that change as a potential presence. The feeling of being watched is your brain's way of prompting you to check, to shift your attention and assess whether there's a threat. But peripheral vision doesn't fully explain the sensation, especially in cases where the person is behind you or completely out of sight. In these situations, the feeling might be the result of other subtle cues. Sound is one. Even if you don't consciously hear footsteps or breathing, your auditory system might pick up faint sounds, the rustle of clothing, a shift in air pressure, the barely perceptible noise of another person's presence. Your brain processes these sounds below the threshold of conscious awareness and uses them to infer that someone is nearby. There's also something called the agency detection system, an evolved cognitive mechanism that makes you hyper-aware of potential agents, beings with intentions and the ability to act. This system is biased toward false positives. In other words, it's better to mistakenly think someone is there when they're not than to fail to notice when they are. If your ancestors heard a rustling in the bushes and assumed it was just the wind, they might miss a predator. But if they assumed every rustling was a threat, they'd survive more often, even if they were wrong most of the time. This bias means your brain is constantly scanning for signs of other people or animals, even when there's no clear evidence. A shadow, an ambiguous sound, a change in light, any of these can trigger the agency detection system, creating the feeling that someone is present. You might interpret this as being watched because the presence of another person often involves their gaze, so the two sensations, presence and being watched, are closely linked in your mind. There's also a social and psychological component. If you're in a situation where you expect to be watched, if you're anxious, if you're in an unfamiliar place, your threshold for detecting presence lowers. Your brain becomes hypervigilant, more likely to interpret ambiguous signals as meaningful. This is why the feeling of being watched is more common when you're alone, in the dark, or in a situation where you feel vulnerable. Your brain is on high alert, and it's primed to detect threats, even if they're not there. Interestingly, studies on gaze detection have shown mixed results. Some research suggests that people can sense when they're being stared at, even when the person is behind them or out of direct view. But these studies are controversial, and many scientists believe the effect is due to subtle cues or biased reporting rather than any kind of extrasensory perception. When controlled experiments are done, where all visual and auditory cues are eliminated, the ability to detect a gaze disappears. What's clear is that the feeling is real, even if the cause is often mundane. Your brain is incredibly good at detecting patterns and inferring the presence of others based on incomplete information. It's a system that evolved to keep you safe, to alert you to potential social interactions or threats before they become obvious. The cost of a false alarm, feeling watched when you're not, is minimal. The cost of missing a real threat is potentially fatal. So your brain errs on the side of caution, creating the sensation of being watched whenever the evidence, however slight, suggests someone might be there. The feeling of being watched is a reminder of how much your brain is processing below the level of conscious awareness. You're not just perceiving the world as it is. You're perceiving your brain's best guess about what's happening, based on sensory input, past experience, and evolutionary programming. And sometimes, that guess includes the presence of unseen eyes, watching from just beyond your field of view. You're sitting still, and suddenly your eyelid starts twitching. Or your calf muscle jumps, a quick, involuntary spasm that you didn't initiate and can't control. It lasts a few seconds, maybe a minute, and then it stops. These random muscle twitches are common, usually harmless, and almost everyone experiences them at some point. But what's actually happening when your muscle decides to move on its own? The immediate cause is a motor neuron firing without your conscious input. Motor neurons are nerve cells that connect your brain and spinal cord to your muscles. When your brain wants you to move, it sends a signal down the motor neuron, which releases neurotransmitters at the junction between the nerve and muscle. These neurotransmitters, primarily acetylcholine, tell the muscle fibers to contract. Normally, this process is tightly controlled, coordinated, and intentional. But sometimes, a motor neuron fires spontaneously, without a command from your brain, causing a muscle to twitch. This spontaneous firing can happen for several reasons. One of the most common is stress. When you're under stress, your body produces higher levels of stress hormones like cortisol and adrenaline. These hormones increase the excitability of your nervous system, making neurons more likely to fire. Your muscles are literally on edge, more reactive, more prone to involuntary contractions. This is why people often notice more twitching during periods of high stress, before an exam, during a busy work period, or in the midst of personal turmoil. Fatigue is another major contributor. When your muscles are tired, either from physical exertion or from prolonged tension, the balance of neurotransmitters at the neuromuscular junction can become disrupted. There might be an excess of acetylcholine, or the muscle fibers might be in a state where they're more sensitive to stimulation. Either way, the result is random, brief contractions that you don't control. This is why twitches are more common in the evening, after a long day, or after intense exercise. Caffeine and other stimulants also increase the likelihood of muscle twitches. Caffeine blocks adenosine, a neurotransmitter that normally has a calming effect on the nervous system. Without adenosine's dampening influence, neurons become more excitable. If you've had too much coffee, energy drinks, or certain medications, you might notice more twitching, particularly in the eyelids, hands, or legs. The effect is temporary and fades as the caffeine is metabolized. Nutritional deficiencies can play a role too. Magnesium, calcium, and potassium are all essential for proper muscle and nerve function. Magnesium, in particular, helps regulate neurotransmitter release and muscle relaxation. If you're low in magnesium, your muscles can become overly excitable, leading to twitching and cramping. Similarly, dehydration can throw off the balance of electrolytes in your body, affecting how nerves and muscles communicate. Most muscle twitches fall under the category of benign fasciculation syndrome. Fasciculation is the medical term for a muscle twitch, and benign means it's not dangerous. These twitches are random, brief, and don't indicate any underlying disease. They're just a normal quirk of the nervous system, especially common in people who are stressed, tired, or overstimulated. The twitches can occur anywhere: eyelids, calves, arms, fingers, and they usually don't last long. They might come and go over days or weeks, often without any clear pattern. However, persistent, widespread muscle twitching can sometimes be a sign of something more serious. Conditions like amyotrophic lateral sclerosis, ALS, or other neuromuscular disorders can cause fasciculations. But these conditions also come with other symptoms: muscle weakness, difficulty moving, changes in coordination. If the twitching is isolated, occasional, and not accompanied by weakness or other neurological symptoms, it's almost always benign. There's also a psychological component. Once you notice a muscle twitch, you often become hyper-aware of it. You start paying close attention to that muscle, and paradoxically, the attention can make the twitching feel more frequent or more intense. This is a form of sensory amplification, where focusing on a sensation makes it more prominent. The twitch might actually be happening at the same rate, but because you're watching for it, it feels worse. For most people, the best approach to dealing with random muscle twitches is to address the underlying factors. Reduce stress through relaxation techniques, exercise, or mindfulness. Get adequate sleep. Cut back on caffeine. Stay hydrated and ensure you're getting enough key nutrients, particularly magnesium. Often, these simple changes are enough to reduce or eliminate the twitching. Muscle twitches are a reminder that your nervous system is always active, always firing, sometimes with perfect precision and sometimes with small, harmless errors. The system is complex and it's not always perfectly controlled. Most of the time, the twitches are just noise, random activity in a busy network of neurons and muscles. They're annoying, but they're not dangerous. They're just your body being slightly imperfect, slightly unpredictable, and ultimately very human. You're aware. You're reading these words, thinking about them, experiencing the sensation of understanding. You have thoughts, feelings, a sense of self. You're conscious. But here's the mystery. You're also a collection of about 86 billion neurons, cells that communicate through electrical and chemical signals. Somehow, from this biological machinery, from neurons firing in patterns, consciousness arises. But how? How does physical matter, tissue, chemicals, electricity, create the subjective experience of being? This is one of the deepest questions in philosophy and neuroscience, often called the hard problem of consciousness. It's not about how the brain processes information. That's the easy problem, relatively speaking. The hard problem is about why and how that processing feels like something from the inside. Why isn't the brain just a biological computer, performing functions without any inner experience? Why is there something it's like to be you? One of the leading theories is neural synchronization. The idea is that consciousness arises when different parts of the brain synchronize their activity, firing together in coordinated patterns. Your brain doesn't process information in one place. Vision happens in the occipital lobe, hearing in the temporal lobe, touch in the parietal lobe, decision-making in the frontal lobe. But your conscious experience feels unified. You don't experience separate streams of sight and sound. You experience a single, integrated reality. This unification is called the binding problem. How does the brain take all these separate processes and bind them into one coherent experience? Neural synchronization offers a possible answer. When neurons in different regions fire in sync, oscillating at the same frequency, they create a temporary network, a coalition of activity that spans multiple brain areas. This synchronized activity might be what creates the unified field of consciousness. The content of your awareness at any given moment is determined by which neurons are firing together at that time. There's evidence for this. Studies using EEG, which measures electrical activity in the brain, have shown that when people are conscious and aware, there's widespread synchronization across the brain, particularly in gamma frequency oscillations, around 40 Hz. During deep sleep or under anesthesia, when consciousness fades, this synchronization decreases. The brain is still active, but the activity is more fragmented, less coordinated. The networks that create conscious experience aren't forming. Another influential theory is integrated information theory, or IIT, developed by neuroscientist Giulio Tononi. IIT proposes that consciousness is a fundamental property of systems that integrate information. The more a system integrates information, the higher its level of consciousness. According to IIT, consciousness isn't something that emerges only in brains. It's a property of any system that meets certain criteria. Specifically, the system must be highly interconnected, with each part influencing many others, and it must generate integrated information, meaning the whole system does something that the parts cannot do in isolation. The brain scores very high on these measures. It's massively interconnected, with neurons forming trillions of connections, and it integrates information constantly, combining sensory input, memory, emotion, and planning into unified experiences and decisions. According to IIT, this is why you're conscious. Your brain creates a high level of integrated information, and that integration is consciousness. IIT also makes a bold claim. Consciousness is a matter of degree. Simple systems like a thermostat or even a single neuron might have a tiny amount of consciousness, far below what we'd recognize or care about. More complex systems like animals with smaller brains have more. Humans with our large, highly interconnected brains have a lot. And if you could build a machine with the same level of integration and connectivity, it would be conscious too. There's also the global workspace theory, which suggests that consciousness is what happens when information becomes globally available across the brain. Most of your brain's activity is unconscious, specialized processes happening in isolation. But when information reaches a certain threshold, it gets broadcast to a global workspace, a network of regions that can all access and work with that information. This broadcast is what makes you consciously aware of it. You become conscious of something when it's no longer confined to a single module, but is instead shared across the whole system, available for reasoning, planning, and verbal report. All of these theories are attempts to bridge the gap between physical processes, neurons, chemicals, electricity, and subjective experience, what it feels like to be you. But none of them fully solve the hard problem. They explain how the brain creates unified, integrated activity. They explain which brain states correspond to consciousness. But they don't explain why that activity feels like anything at all. Why does synchronization or integration or global broadcasting create an inner world of experience? Why isn't it all just dark, just processing, without any subjective quality? Some philosophers, like David Chalmers, argue that this gap might never be bridged by neuroscience alone. Consciousness might be a fundamental feature of reality, like space or time, something that can't be fully explained in terms of something else. Others believe that as we learn more about the brain, the mystery will dissolve. We'll realize that consciousness is just what certain kinds of information processing feel like from the inside. What's clear is that consciousness depends on the brain. Damage certain areas, and aspects of consciousness disappear. Alter brain chemistry, and your experience changes. But the relationship between brain activity and subjective experience remains one of the most profound mysteries in science. The fact that you're aware, that you're experiencing this moment right now, is both the most obvious thing in your life and one of the hardest things to explain. Look at your fingertips. Those swirling patterns of ridges and valleys are completely unique to you. No one else in the world has the same fingerprints, not even identical twins. For centuries, humans have used this uniqueness for identification, from ancient seal stamps to modern biometric security. But fingerprints didn't evolve to help solve crimes or unlock phones. They serve a much more practical physical purpose. So why do we have them? The most obvious function is grip. The ridges on your fingertips aren't smooth. They create friction between your skin and whatever you're touching. This increased friction makes it easier to hold onto objects, especially smooth or slippery ones. Without fingerprints, your fingers would be like smooth rubber, functional but far less effective at maintaining a secure grip. The ridges work like the treads on a tire, channeling away moisture and increasing contact with the surface. But there's more to it than just friction. Research has shown that fingerprints also improve tactile sensitivity, your ability to detect fine textures and subtle vibrations. When you run your finger across a surface, the ridges amplify the vibrations created by the interaction. These vibrations travel through your skin to the mechanoreceptors underneath, specialized nerve endings that detect touch, pressure, and texture. The ridges essentially act as amplifiers, enhancing the signal these receptors receive. This amplification is particularly useful for detecting fine details. When you touch fabric, for example, your fingerprints help you distinguish between silk and cotton, between rough and smooth. The ridges catch on the tiny fibers, creating distinct vibration patterns that your brain interprets as texture. Without fingerprints, your sense of touch would be significantly dulled. You'd still feel pressure and temperature, but the nuanced information about surface texture would be largely lost. The development of fingerprints is a fascinating process that begins in the womb. Around the 10th week of pregnancy, the fetus's fingers start developing raised pads called volar pads. As the fetus grows, these pads gradually flatten, but the timing and pattern of this flattening are influenced by several factors: the growth rate of different skin layers, the shape of the underlying bone, and even the position of the baby in the womb. The skin doesn't just flatten uniformly. It buckles and folds, creating the ridges and valleys that become fingerprints. Because this process is influenced by so many variables, including random fluctuations in the womb environment, the exact pattern is unique every time. Even identical twins, who share the same DNA, develop different fingerprints because their development is influenced by slightly different positions, movements, and growth rates in the womb. The patterns are determined partly by genetics, which is why family members often have similar general patterns, like loops or whorls, but the specific details are entirely individual. The patterns themselves fall into three main categories: loops, whorls, and arches. About 60–70% of people have loops, where the ridges enter from one side, curve around, and exit from the same side. Whorls, which account for about 25–35% of fingerprints, form circular or spiral patterns. Arches, the rarest at about 5%, rise in the center and slope down on both sides. These patterns are determined by the shape and size of the volar pads during development. Larger pads tend to create whorls, while smaller pads produce arches. Interestingly, fingerprints aren't the only place where we have these ridges. Your palms, toes, and the soles of your feet all have similar patterns, though they're less distinct. These ridges serve the same functions, improving grip and enhancing touch sensitivity. They're especially important on the feet, where they help with balance and traction when walking on uneven or slippery surfaces. There's also an evolutionary perspective. Primates, our closest relatives, also have fingerprints, and they serve similar functions. For tree-dwelling ancestors, secure grip and sensitive touch would have been critical for survival, navigating branches, grasping food, and detecting threats. The development of fingerprints likely provided a significant advantage, making fine motor control and tactile exploration more effective. Some researchers have proposed additional functions. One hypothesis suggests that fingerprints might help channel away water, similar to how tire treads prevent hydroplaning. When your fingers get wet, the ridges create channels that allow water to escape from under your fingertip, maintaining contact with the surface. Another theory suggests that the ridges protect the underlying skin from damage by distributing stress more evenly across the fingertip. Fingerprints also play a role in thermoregulation, helping to dissipate heat and moisture from the hands. The increased surface area created by the ridges allows for more efficient cooling and drying, which could be important during activities that generate heat and sweat. What's clear is that fingerprints are far from decorative. They're functional biomechanical features that enhance two of the most important aspects of hand use: grip and touch. They're a product of complex developmental processes, shaped by both genetics and the random fluctuations of growth in the womb. And while their uniqueness has made them invaluable for identification, their real purpose is much more fundamental, helping you hold, feel, and interact with the physical world. You wake up naturally at 6 a.m., alert and ready to go. You're most productive in the early hours, and by 10 p.m. you're already winding down. Meanwhile, your friend can barely function before noon, hits their stride in the afternoon, and feels most alive at midnight. Neither of you is broken. You're just wired differently. But why do some people thrive in the morning while others are night owls? The answer is chronotype, your body's natural preference for when to sleep and wake. Chronotype is largely determined by genetics, specifically by variations in genes that regulate your circadian rhythm, the internal 24-hour clock that controls sleep-wake cycles, hormone release, body temperature, and other biological processes. Your circadian rhythm is run by a master clock in the brain, located in the suprachiasmatic nucleus, but the rhythm itself is influenced by dozens of genes. One of the most studied is the PER3 gene, which produces a protein involved in regulating the circadian clock. There are two main variants of this gene, a longer version and a shorter version. People with the longer variant tend to be morning people. They naturally wake earlier, are more alert in the morning, and prefer to go to bed earlier. People with the shorter variant tend to be evening people. They wake later, feel groggy in the morning, and are more alert and energetic as the day progresses. This isn't just about preference. It's about biology. Morning people, or larks, have circadian rhythms that run slightly shorter than 24 hours, meaning their internal clock naturally wants to wake them up earlier. Night owls, or evening types, have rhythms that run slightly longer than 24 hours, pushing their sleep schedule later. Over time, without external cues like alarm clocks or work schedules, morning people would naturally drift toward earlier sleep and wake times, while night owls would drift later. There are other genes involved too. Clock and BMAL1 regulate the production of circadian proteins. Variations in these genes can affect whether you're naturally inclined to wake early or stay up late. The whole system is incredibly complex, involving feedback loops where certain proteins build up during the day, promoting wakefulness, and then break down at night, allowing sleep to occur. Genetic differences can shift the timing of these cycles, making you feel alert at different times than someone else. But genetics isn't the whole story. Age plays a significant role. Chronotype changes over your lifespan. Children are generally morning types, which is why kids often wake up absurdly early on weekends. But as you enter adolescence, there's a dramatic shift toward eveningness. Teenagers naturally want to stay up late and sleep late. This isn't laziness or rebellion. It's a biological shift in circadian timing that happens during puberty, driven by hormonal changes. This shift continues into the early 20s and then gradually reverses. As people age into their 30s, 40s, and beyond, they tend to shift back toward morningness. Older adults are often the earliest risers, waking naturally at dawn or even before. This pattern is universal across cultures, suggesting it's a fundamental feature of human development, not a product of modern schedules or lifestyle. Environment also plays a role. Exposure to light is the most powerful external cue for the circadian system. Light, especially blue wavelength light from the sun, signals to the suprachiasmatic nucleus that it's daytime, which suppresses melatonin production and promotes wakefulness. If you consistently expose yourself to bright light in the morning, you can shift your circadian rhythm earlier, making it easier to wake up. Conversely, exposure to light late in the evening, especially from screens, can shift your rhythm later, reinforcing night owl tendencies. Cultural and lifestyle factors matter too. Work schedules, social obligations, and personal habits can all push against your natural chronotype. A night owl forced to wake at 6 a.m. for work every day is essentially in a state of chronic circadian misalignment, often called social jet lag. They're fighting their biology, and over time, this can lead to sleep deprivation, mood issues, and health problems. Morning people forced to stay up late face similar challenges, though they're less common because society tends to favor early schedules. Research has shown that chronotype affects more than just sleep. It influences cognitive performance, mood, and even personality. Morning people tend to be more conscientious and proactive. They're better at planning and following through on tasks. Evening people tend to be more creative and open to new experiences. They perform better on tasks requiring cognitive flexibility and problem solving, especially later in the day. Neither type is superior. They're just optimized for different times. There's also evidence that chronotype might have evolutionary roots. Having a mix of morning people and night owls in a group could have been advantageous for early human societies. Some people would naturally be alert in the early morning, keeping watch and starting tasks. Others would stay alert late into the night, guarding against threats and managing evening activities. This diversity in sleep schedules could have provided round-the-clock vigilance, increasing the group's chances of survival. Understanding your chronotype is important because it affects your quality of life. Trying to force yourself into a schedule that doesn't match your biology is exhausting and often counterproductive. When possible, aligning your schedule with your natural rhythms, waking when your body wants to wake, working when you're most alert, leads to better sleep, better performance, and better overall well-being. You're not lazy if you're not a morning person. You're just listening to a different internal clock. Right now, as you read this, your brain is being bombarded with information. The words on the screen, the feeling of the chair beneath you, the temperature of the room, distant sounds, the pressure of your clothes, your heartbeat, the sensation of breathing. Your senses are constantly feeding your brain far more data than you could possibly process consciously. So how does your brain decide what to focus on and what to ignore? The answer begins with a structure called the reticular activating system, or RAS. This is a network of neurons located in the brainstem, at the base of your brain where it connects to the spinal cord. The RAS acts as a gatekeeper, filtering sensory information before it reaches your conscious awareness. It's constantly scanning incoming signals and making split-second decisions about what's important enough to pass through to higher brain areas and what can be safely ignored. The RAS doesn't evaluate importance randomly. It uses several criteria. One of the most important is novelty. Anything new, unexpected, or different from the background automatically gets flagged. This is why you immediately notice when a sound stops, like when a humming refrigerator shuts off, even though you weren't consciously aware of the hum before. Your brain was monitoring it in the background, and the change triggered the RAS to bring it to your attention. Another key criterion is salience, how relevant or significant something is to your current goals, needs, or survival. Salience isn't fixed. It changes based on context. If you're hungry, food-related words and images suddenly become more noticeable. If you're anxious about something, anything related to that concern grabs your attention more easily. The RAS is constantly adjusting what counts as important based on your internal state. Threat detection is a high-priority signal for the RAS. Anything that could indicate danger, a loud noise, sudden movement, someone saying your name in an angry tone, gets immediate attention. This is an evolutionary adaptation. Missing a threat could be fatal, so the brain errs on the side of caution, interrupting whatever you're doing to assess potential danger. There's also something called the cocktail party effect, which demonstrates how sophisticated your attention system really is. Imagine you're at a crowded party, surrounded by dozens of conversations happening simultaneously. You're talking to someone, focused on their voice, and somehow your brain is filtering out all the other noise. But then, across the room, someone mentions your name. Instantly, your attention shifts. You weren't consciously listening to that other conversation, but your brain was monitoring it at a low level, and when it detected something highly relevant, your name, it pulled your focus. This effect shows that your brain processes far more information than you're aware of. The RAS and associated attention networks are constantly scanning all incoming sensory input, even what you're not consciously attending to, looking for signals that meet the criteria for importance. When something matches, attention shifts automatically, often before you're even aware of making a decision. The prefrontal cortex also plays a critical role in attention, but in a different way. While the RAS handles automatic bottom-up attention, your prefrontal cortex manages top-down attention, the kind you control deliberately. When you decide to focus on reading, ignore your phone, or concentrate on a specific task, that's your prefrontal cortex exerting control, suppressing irrelevant information and enhancing signals related to your goal. But top-down attention is effortful. It requires mental resources, and it's easily disrupted. This is why multitasking is so difficult. Your prefrontal cortex can only maintain strong focus on one thing at a time. When you try to split attention between two demanding tasks, performance on both suffers because your brain is constantly switching between them, and each switch comes with a cost. There's also a phenomenon called attentional capture, where certain stimuli are so powerful that they override your top-down control. Flashing lights, loud noises, sudden movements, these are hard to ignore because they trigger strong bottom-up signals that hijack attention. Advertisers and interface designers exploit this, using bright colors, motion, and contrast to capture attention, even when you're trying to focus on something else. Attention is also influenced by fatigue and stress. When you're tired or overwhelmed, your prefrontal cortex's ability to maintain top-down control weakens. You become more distractible, more vulnerable to irrelevant stimuli. The RAS still functions, but without strong top-down regulation, attention becomes more scattered, jumping from one thing to another without settling. What makes attention fascinating is that it's both automatic and controlled, both passive and active. You're constantly being pulled by salience, novelty, and threat, but you also have the ability to direct your focus deliberately. The balance between these two systems, bottom-up and top-down, determines what you experience as reality in any given moment. Your conscious experience isn't the raw sensory data. It's the filtered, selected, prioritized subset that your attention systems decide is worth your awareness. Everything else fades into the background, unnoticed but not necessarily unprocessed, waiting for a reason to become important. You scrape your knee or get a minor cut. For the first day or two, it hurts. But then, as it starts to heal, a new sensation takes over: itching. Deep, persistent, almost unbearable itching. You know you shouldn't scratch, but the urge is overwhelming. Why do healing wounds itch so intensely? The answer lies in the biology of tissue repair. When your skin is damaged, your body immediately launches a complex healing process involving multiple stages: inflammation, tissue formation, and remodeling. Each stage involves different cells, chemicals, and signals, and many of these directly trigger the sensation of itching. The first culprit is histamine. This is a chemical released by mast cells, a type of immune cell, during the inflammatory phase of healing. Histamine's primary job is to increase blood flow to the injured area, bringing in immune cells and nutrients needed for repair. It does this by making blood vessels more permeable, which causes the redness and swelling you see around a fresh wound. But histamine also binds to receptors on nerve endings in the skin, and when it does, it triggers the sensation of itching. This is the same mechanism behind allergic reactions. When you have an allergic response, mast cells release large amounts of histamine, causing intense itching along with other symptoms. In the context of wound healing, the histamine release is more localized and controlled, but the effect on nerve endings is the same. The itch is your body's way of signaling that something is happening in that area, that the repair process is active. As healing progresses, new tissue begins to form. Fibroblasts, cells that produce collagen, migrate into the wound and start building the structural framework for new skin. At the same time, nerve endings that were damaged or severed during the injury begin to regenerate. This nerve regrowth is another major source of itching. As new nerve fibers extend into the healing tissue, they're hypersensitive, firing more easily in response to stimuli that wouldn't normally trigger them. This increased sensitivity translates into sensations that your brain often interprets as itching. There's also inflammation. The healing process involves a controlled inflammatory response, where immune cells release various chemicals to fight infection and clear debris. Some of these chemicals, cytokines and prostaglandins for example, can activate nerve endings and contribute to the itching sensation. The inflammation isn't harmful. It's essential for proper healing, but it comes with side effects, and itching is one of them. Dry skin around the wound also contributes. As new skin forms, it's often drier and tighter than the surrounding tissue. This dryness can irritate nerve endings and add to the itching. The edges of the wound, where new skin is actively growing, are particularly prone to this because the skin there is still forming its protective outer layer and hasn't yet developed the normal moisture barrier. Scabs, the hard crusts that form over wounds, play a role too. As a scab dries and contracts, it pulls on the surrounding skin, creating tension. This mechanical stimulation of nerve endings can be perceived as itching. The scab is also a foreign presence on the skin, and your brain receives constant signals about it, signals that often get interpreted as an itch that needs to be scratched. Scratching, of course, is the worst thing you can do. It can reopen the wound, introduce bacteria, damage the delicate new tissue, and even lead to scarring. But the urge is so strong because itching and pain are closely related. They're both processed by similar nerve pathways, and scratching provides temporary relief by overwhelming the itch signals with pain signals. Your brain prioritizes the sharper, more immediate sensation of scratching over the persistent itch, creating a brief sense of relief. But it's short-lived, and the damage you cause can prolong healing and make the itching worse in the long run. The intensity of itching varies depending on the type and location of the wound. Wounds on areas with more nerve endings, like the face or hands, tend to itch more. Deeper wounds, which involve more tissue damage and a longer healing process, also tend to itch more intensely and for a longer period. Interestingly, not all itching during healing is bad. It's a sign that the repair process is working, that blood flow is adequate, that new tissue is forming, and that nerves are regenerating. In a sense, itching is a positive signal, an indication that your body is doing what it needs to do to restore the damaged area. Managing the itch is about supporting the healing process while minimizing discomfort. Keeping the wound clean and moisturized can help reduce dryness and irritation. Antihistamines can reduce the histamine-related itching, though they're usually only necessary for more severe cases. Cool compresses can provide temporary relief by numbing the area slightly. And most importantly, resisting the urge to scratch allows the healing to proceed without interruption. Itching during healing is uncomfortable, but it's a reminder that your body is actively repairing itself. The signals that create the itch, histamine, inflammation, nerve regrowth, are all part of a carefully orchestrated process designed to restore your skin to its original state. The itch is just the side effect of that restoration, a temporary annoyance that signals progress. You take a big bite of ice cream or a long sip of a frozen drink. For a moment, everything is fine. Then it hits, a sharp, intense pain in your forehead, right between your eyes or at the temples. It's sudden, almost debilitating, and it lasts for 10 to 30 seconds before fading as quickly as it came. This is brain freeze, and despite the name, your brain isn't actually freezing. So what's really happening? The technical term is sphenopalatine ganglioneuralgia, which essentially means nerve pain in the sphenopalatine ganglion. The sphenopalatine ganglion is a bundle of nerves located at the roof of your mouth, toward the back of your palate. When something very cold touches this area, like ice cream or a cold beverage, it triggers a rapid temperature change in the tissue. Your body is extremely sensitive to temperature changes, especially in areas close to the brain. The rapid cooling of the palate causes the blood vessels in that region to constrict quickly, narrowing to reduce blood flow and conserve heat. But within seconds, as your body tries to correct the temperature drop, those same blood vessels dilate rapidly, expanding to increase blood flow and warm the area back up. This rapid dilation is the primary cause of the pain. When blood vessels expand quickly, they can trigger pain receptors in the surrounding tissue. The dilation also increases pressure in the area, and this pressure is transmitted through nerves that connect to your head and face. The pain you feel isn't actually in your palate. It's referred pain, a phenomenon where discomfort from one area is perceived in another. The nerves in your palate, particularly the trigeminal nerve, one of the largest nerves in your head, are highly sensitive. When they detect the rapid temperature change and vascular activity, they send signals to your brain. But because the trigeminal nerve also serves your forehead, temples, and face, your brain misinterprets the location of the pain. Instead of feeling it in the roof of your mouth, you feel it in your forehead or behind your eyes. This is the same mechanism that causes referred pain in other parts of the body, like when heart problems cause pain in the left arm. The phenomenon is more likely to happen when you consume cold foods or drinks quickly. If you eat ice cream slowly, giving your palate time to adjust to the temperature gradually, you're less likely to trigger the rapid vascular response that causes brain freeze. But when you gulp a cold drink or take a large bite of frozen dessert, the sudden temperature shock is more intense, and the response is stronger. Not everyone gets brain freeze, and those who do experience it with varying intensity. Some people are more sensitive to temperature changes, or their blood vessels respond more dramatically. There's also evidence that people who suffer from migraines are more prone to brain freeze, possibly because their vascular systems are more reactive or their pain pathways are more sensitive. The pain, while intense, is harmless. It's not causing any damage to your brain or nerves. It's just a temporary overreaction by your vascular system to an unexpected cold stimulus. The fact that it resolves so quickly, usually within 30 seconds, is a sign that your body is rapidly correcting the situation. Once the temperature normalizes and the blood vessels stabilize, the pain signals stop. There are a few ways to prevent or alleviate brain freeze. The most obvious is to eat or drink cold things more slowly, giving your palate time to adjust. If you do get brain freeze, pressing your tongue flat against the roof of your mouth can help. The warmth from your tongue speeds up the rewarming process, helping the blood vessels return to normal faster. Drinking a room temperature beverage can also help by directly warming the palate. Some people also find that breathing through their mouth or covering their mouth and nose and breathing rapidly can reduce the intensity or duration of brain freeze. These methods work by warming the air reaching your palate, counteracting the cold stimulus. Brain freeze is a perfect example of how interconnected your body systems are. A cold sensation in your mouth triggers a vascular response, which activates nerves that extend throughout your head, resulting in pain that feels like it's coming from your brain. The pain is real, the cause is local, and the solution is simple. Slow down and let your body adjust to the temperature. A baby is born into a world of sound. Voices, music, traffic, the hum of everyday life. Within months, that baby begins to distinguish speech from other sounds. By their first birthday, they're saying words. By age 3, they're speaking in sentences, using grammar rules they've never been explicitly taught. No one sits down with a baby and explains verb conjugation or sentence structure, yet somehow, almost every child masters the complex system of their native language. How? The process begins even before birth. Fetuses can hear sounds from outside the womb, and they're already tuning in to the rhythm and melody of their mother's voice. Studies have shown that newborns prefer their mother's voice over others, and can distinguish their native language from foreign languages based purely on prosody, the musical quality of speech. This early exposure primes the brain for language learning, establishing foundational patterns before the baby ever speaks. One influential theory, proposed by linguist Noam Chomsky, is the universal grammar hypothesis. Chomsky argued that humans are born with an innate capacity for language, a kind of pre-wired grammar template in the brain. According to this view, all human languages share deep structural similarities, and babies come equipped with the mental tools to detect and learn these structures. They don't start from scratch. They start with a blueprint, and exposure to language fills in the specific details of their native tongue. Evidence for this comes from the speed and consistency of language acquisition. Children around the world, regardless of the language they're learning, go through similar stages at similar ages. They babble, then speak single words, then combine words, then master complex sentences. They make similar types of errors, like overregularizing grammar rules, I goed, instead of I went. These patterns suggest that there's something universal about how the human brain approaches language. But innate structure is only part of the story. Bobbies are also incredibly powerful statistical learners. Their brains are constantly analyzing the input they receive, detecting patterns in the sounds, words, and structures around them. This isn't conscious analysis. It's automatic, happening below the level of awareness. When a baby hears speech, their brain is tracking which sounds occur together, which words follow other words, and which patterns repeat. This statistical learning is astonishingly effective. In one famous experiment, 8-month-old bobbies were exposed to a stream of nonsense syllables for just a few minutes. The syllables were arranged so that certain combinations always appeared together, forming words, while other combinations were random. After this brief exposure, the bobbies could distinguish the words from random syllables, showing that they detected the statistical patterns without any explicit instruction. This ability to extract structure from input is foundational to language learning. The brain's capacity for language learning is highest during the critical period, roughly from birth to puberty. During this window, the brain is extraordinarily plastic, meaning it's highly adaptable and capable of forming new connections rapidly. Neural circuits for language are being built and refined based on input. Children exposed to language during this period absorb it effortlessly, often becoming fully fluent in multiple languages if they're exposed to them simultaneously. After puberty, this plasticity decreases. Learning a new language becomes harder, more effortful, and usually results in less native-like proficiency. This doesn't mean adults can't learn languages, they can, but they rely more on explicit instruction and conscious effort, whereas children learn implicitly, through exposure and interaction. The critical period exists because the brain is organizing itself based on the input it receives. Neurons that fire together wire together, and during early development, the connections that are used frequently are strengthened, while those that aren't used are pruned away. If a child isn't exposed to language during the critical period, as in tragic cases of severe neglect, they often fail to fully acquire language later, even with intensive instruction. This shows that timing matters. The brain has a window when it's optimized for language, and that window eventually closes. Bobbies also benefit from the way adults naturally speak to them. Across cultures, caregivers tend to use parentese or baby talk, characterized by higher pitch, exaggerated intonation, slower tempo, and simpler grammar. This isn't just cute, it's functional. The exaggerated features make it easier for bobbies to detect word boundaries, distinguish sounds, and focus on important elements of speech. Studies show that bobbies pay more attention to parentese and learn language faster when it's used. Social interaction is crucial too. Bobbies don't learn language effectively from passive exposure alone, like from television or recordings. They need back-and-forth interaction, where they hear language in context, see facial expressions, and receive feedback. This social engagement helps them map sounds to meanings, understand that words refer to things and actions, and grasp the communicative purpose of language. Mirror neurons may also play a role. When a baby watches someone speak, neurons in their own motor areas activate as if they were making the same movements. This neural mirroring might help bobbies learn the motor patterns of speech, connecting what they hear to how to produce it themselves. By around 12 months, most bobbies say their first words, but comprehension precedes production by months. Bobbies understand far more than they can say, showing that receptive language develops first. As they continue to hear language, their vocabularies explode. By age 2, many children are learning several new words a day, a process called fast mapping, where they can infer the meaning of a new word from just 1 or 2 exposures in context. Grammar acquisition follows a similar pattern. Children start combining words around 18 to 24 months, creating simple 2-word phrases like more milk or daddy go. These early sentences lack grammatical markers like articles or verb endings, but they convey meaning. Over the next few years, children gradually add complexity, incorporating tenses, plurals, pronouns, and subordinate clauses. They don't learn rules explicitly. They extract them from the patterns they observe in the speech around them. What makes this process so remarkable is that it happens with noisy, imperfect input. Real speech is full of errors, false starts, interruptions, and variations, yet children reliably extract the underlying system. Their brains are designed to filter out the noise and focus on the consistent patterns, building a mental model of language that allows them to generate and understand an infinite number of sentences they've never heard before. Language acquisition is one of the most impressive cognitive achievements of early childhood, a testament to the brain's incredible capacity for learning, pattern detection, and adaptation during the critical early years. You're listening to a song, and suddenly a powerful chord progression or a soaring vocal line hits you. A wave of sensation rushes over your skin. The hairs on your arms and the back of your neck stand up. You might shiver, even though you're not cold. This experience is called frisson, a French word meaning shiver, and it's one of the most fascinating responses your body has to art. But why does music, which is just organized sound, trigger a physical reaction that's usually associated with cold or fear? Frisson is a complex response involving multiple brain systems. When you hear music that moves you, several things happen at once. First, your auditory cortex processes the sound, analyzing pitch, rhythm, and timbre. But the signal doesn't stop there. It spreads to areas involved in emotion and reward, particularly the limbic system, which includes the amygdala and the nucleus accumbens, a key region in the brain's reward circuit. When music triggers an emotional response, the nucleus accumbens releases dopamine, the same neurotransmitter associated with pleasure, motivation, and reward. Brain imaging studies have shown that the moments when people experience frisson correspond to spikes in dopamine release. This isn't background dopamine. It's a surge, similar to what you might experience from eating delicious food, achieving a goal, or receiving unexpected good news. The music is essentially hijacking your reward system. But dopamine alone doesn't fully explain frisson. The physical sensation, the goosebumps and shivering, is controlled by the autonomic nervous system, the same system that regulates your fight or flight response. When the music reaches a particularly emotional or unexpected moment, your sympathetic nervous system activates slightly. Your heart rate might increase, your pupils might dilate, and the tiny muscles at the base of each hair follicle, called erector pili muscles, contract, causing the hairs to stand up. This response is called piloerection, and it's an evolutionary remnant. In many mammals, piloerection serves a function. When a cat is frightened or trying to appear larger, its fur stands on end. When you're cold, goosebumps create a layer of insulation by trapping air near the skin. But humans have lost most of our body hair, so the response no longer serves these practical purposes. Instead, it lingers as a vestigial reflex, triggered not by cold or threat, but by intense emotion. The question is, why does music trigger this ancient response? One theory is that music taps into the same neural pathways that signal important emotional or social events. In evolutionary terms, emotional arousal was often linked to survival-relevant situations: danger, social bonding, group cohesion. Music, especially when performed in groups or experienced communally, might activate these same pathways because it signals something socially or emotionally significant. Certain musical features are more likely to induce frisson. Sudden changes in dynamics, like a shift from soft to loud, often trigger it. Unexpected harmonic progressions or resolutions can do it too. A singer's voice cracking with emotion, a climactic instrumental moment, the entrance of a choir, these are all common triggers. What they share is a violation of expectation. Your brain is constantly predicting what will happen next in the music, and when the music surprises you in a particularly effective way, it creates a powerful emotional response. This is tied to how the brain processes music. Listening to music isn't passive. Your brain is actively engaged, tracking patterns, anticipating what comes next, and feeling satisfaction when predictions are confirmed or surprise when they're violated. The most powerful musical moments often combine both. They build expectation and then resolve or subvert it in a way that feels both surprising and inevitable. Individual differences matter too. Not everyone experiences frisson, and among those who do, the triggers vary. People who are more open to new experiences, a personality trait associated with creativity and imagination, report more frequent frisson. Musicians and people with musical training also tend to experience it more often, possibly because they're more attuned to the structural and emotional nuances of music. There's also a social and cultural component. Music that's deeply connected to personal memories or cultural identity is more likely to trigger frisson. A song from your childhood, a piece tied to a significant moment in your life, or music that represents your community or heritage can all elicit strong emotional responses. The frisson isn't just about the notes. It's about the associations, the meaning the music carries. The neurochemical response to music goes beyond dopamine. Oxytocin, a hormone associated with bonding and trust, can also be released during musical experiences, especially in group settings like concerts or communal singing. Endorphins, the body's natural painkillers, are released as well, contributing to the euphoric feeling that music can create. Interestingly, frisson is more common during live performances than recorded music. The presence of other people, the visual element of seeing musicians perform, and the shared emotional experience all enhance the response. Music is fundamentally social, and experiencing it with others amplifies its emotional impact. Some researchers believe that music's power over our emotions is related to its ability to mimic the prosody of emotional speech. A sad melody might have the same contours as a lamenting voice. An energetic rhythm might resemble excited speech. Your brain, which is finely tuned to interpret vocal emotion, responds to these patterns in music as if they're communicating something emotionally significant. Frisson is a reminder that music isn't just entertainment. It's a deeply emotional, physiological experience. It engages your brain's reward system, activates ancient reflexes, and connects you to something larger than yourself. The goosebumps you feel are your body responding to beauty, to surprise, to the profound human capacity to create and experience art. It's evolution and emotion, biology and culture, all converging in a shiver that runs down your spine. You're driving and suddenly the car in front of you slams on its brakes, or you're falling and the ground is rushing up to meet you. In that moment, time seems to slow down. You perceive everything in vivid detail as if each second is stretching out, giving you time to react, to think, to feel the full weight of what's happening. But when it's over, when you're safe, you realize only a few seconds passed. Why does time seem to expand during moments of extreme stress or danger? The phenomenon is linked to how your brain processes and encodes memories during high-stress situations. Under normal circumstances, your brain is selective about what it records. Most experiences are encoded with moderate detail, enough to remember the general outline but not every tiny element. But when you're in danger, when your survival might depend on your next action, your brain shifts into a different mode. The amygdala, your brain's fear and emotion center, becomes hyperactive during threatening situations. It's the amygdala's job to detect danger and coordinate your body's response, activating the fight or flight system, increasing heart rate, sharpening focus, and preparing you to act. But the amygdala also plays a crucial role in memory formation. When it's highly activated, it signals to the hippocampus and other memory systems that this moment is important, that it needs to be encoded in detail. During these high arousal moments, your brain records far more information than usual. It captures sensory details, your surroundings, sounds, physical sensations with greater precision. It also increases the temporal resolution of your perception, essentially taking more snapshots per second. This enhanced encoding creates a richer, denser memory of the event. Here's where the time distortion comes in. The feeling that time slowed down is actually a memory illusion. In the moment, time didn't actually slow. Your perception was operating at normal speed. But because your brain was recording so much more information than usual, when you recall the event later, there's more detail to unpack. The memory feels longer because it contains more data. Your brain interprets this dense memory as having taken more time than it actually did. This has been demonstrated experimentally. Researchers have tested whether people can actually perceive time differently during high-stress moments by having participants free fall while trying to read rapidly flashing numbers. If time truly slowed down for them, they should have been able to read numbers flashing too fast to see under normal conditions. But they couldn't. Their perception in the moment wasn't enhanced. What was enhanced was their memory of the event, which made it feel, in retrospect, like time had slowed. The survival value of this system is clear. In dangerous situations, having detailed memories can be life-saving. If you narrowly avoid a car accident, your brain's detailed recording of the event helps you learn from it. You remember exactly what went wrong, what signs you missed, what actions you took. This detailed memory increases your chances of avoiding similar situations in the future. There's also a heightened state of attention during these moments. Your brain suppresses non-essential processes and focuses intensely on the threat. This narrowing of attention, sometimes called tunnel vision, makes the experience feel more vivid and immersive. You're not distracted by irrelevant details. Everything becomes about the immediate situation. This intense focus contributes to the sense that time is moving differently, because you're processing the moment with a level of awareness that's far above your everyday baseline. Neurochemically, your body is flooded with stress hormones, primarily adrenaline and cortisol. These hormones enhance memory consolidation, making the experience more likely to be stored in long-term memory. Adrenaline also increases alertness and sharpens sensory perception, which contributes to the vividness of the memory. The combination of heightened perception, enhanced encoding, and stress hormone release creates a memory that stands out dramatically from ordinary experiences. Interestingly, not all stressful moments produce this effect. The time distortion is most pronounced during sudden, acute threats, situations where survival is immediately at stake. Chronic stress or prolonged danger doesn't have the same impact. The system is designed for brief, intense moments of crisis, not extended periods of adversity. The phenomenon also varies between individuals. People who have experienced trauma or who have been in many high-stress situations sometimes report that the effect diminishes over time. This might be because their amygdala becomes less reactive, a form of adaptation, or because they've developed coping mechanisms that allow them to remain calmer during stressful events. There's a philosophical dimension to this as well. The fact that time can feel so radically different in extreme moments reveals how subjective our experience of time really is. Time, as we perceive it, isn't a fixed, objective flow. It's constructed by our brains based on the density and quality of our experiences. A boring hour can feel like forever because little is being encoded. A terrifying few seconds can feel like minutes because so much is being captured. This distortion is a powerful reminder of the brain's flexibility and its prioritization of survival. When the stakes are highest, when your life might depend on it, your brain pulls out all the stops, recording everything, sharpening focus, and creating a memory so vivid that it warps your sense of time itself. The moment doesn't actually last longer, but it's remembered as if it did, and in the currency of experience, that's what matters. Every second your immune system is making life-or-death decisions. It's scanning your body, checking every cell, every protein, every molecule it encounters and asking the same question: is this me or is this something else? If it's foreign, a virus, bacterium, or abnormal cell, the immune system attacks. If it's you, it leaves it alone. This distinction is critical. Get it wrong and the consequences are severe. Fail to attack a pathogen and you get sick. Attack your own cells, and you develop an autoimmune disease. So how does the immune system know what belongs and what doesn't? The answer begins early in development, particularly in an organ called the thymus, a small gland located behind your breastbone. The thymus is where T cells, one of the most important types of immune cells, go through their education. T cells are born in the bone marrow, but they're sent to the thymus to learn the difference between self and non-self. In the thymus, developing T cells are exposed to samples of your body's own proteins, presented by specialized cells. Each T cell has receptors on its surface that can bind to specific molecular patterns. The T cells are tested. If their receptors bind strongly to self-proteins, they fail the test. These cells are dangerous because they're reactive to your own body, so they're either killed or rendered inactive. This process is called negative selection, and it eliminates the vast majority of developing T cells. The ones that survive are those whose receptors don't react strongly to self. They've passed the test. They're allowed to leave the thymus and enter circulation, ready to detect foreign invaders. But even after leaving the thymus, T cells are kept in check. They require multiple signals to become fully activated, a safeguard against accidental attacks on healthy tissue. But education alone isn't enough. The immune system also uses molecular markers to identify cells. Every nucleated cell in your body displays proteins on its surface called MHC molecules, short for major histocompatibility complex. There are two classes: MHC class I, found on almost all cells, and MHC class II, found on specialized immune cells. These MHC molecules present small fragments of proteins from inside the cell, like a display window showing what's happening internally. Under normal conditions, MHC molecules present fragments of your own proteins, self-peptides. Immune cells see these and recognize them as normal. But if a cell is infected by a virus, or if it's become cancerous, the MHC molecules present foreign or abnormal peptides. T cells patrol constantly, checking these displays. When they encounter an MHC molecule presenting something that looks foreign, they investigate further. If the cell is confirmed as infected or abnormal, the T cell initiates an attack, either killing the cell directly or recruiting other immune cells to help. This system is elegant but not perfect. Autoimmune diseases occur when the education process fails, when T cells that react to self escape elimination, or when the regulatory mechanisms that suppress them break down. In conditions like type 1 diabetes, rheumatoid arthritis, or multiple sclerosis, the immune system mistakenly attacks healthy tissue, treating it as foreign. There are also regulatory T cells, a subset that specializes in calming immune responses and preventing attacks on self. These cells patrol the body, actively suppressing immune activity that targets normal tissue. They're essential for maintaining tolerance, the state of not attacking your own cells. When regulatory T cells malfunction, autoimmunity becomes more likely. The MHC system is also why organ transplants are so challenging. MHC molecules are highly variable between individuals, encoded by genes that are among the most diverse in the human genome. This diversity is beneficial for populations. It means pathogens can't easily evade everyone's immune system, but it creates problems for transplants. If you receive an organ from someone with different MHC molecules, your immune system sees those cells as foreign and attacks them, leading to rejection. This is why transplant recipients need immunosuppressive drugs to prevent their immune system from destroying the donated organ. Identical twins who share the same MHC molecules can donate organs to each other without rejection. For everyone else, doctors try to match MHC types as closely as possible, but perfect matches are rare outside of close relatives. The immune system also uses pattern recognition receptors, proteins that detect molecular patterns common to pathogens but absent in human cells. For example, bacterial cell walls contain molecules that human cells don't have. When immune cells detect these patterns, they know immediately that something foreign is present, and they respond accordingly. There's also a concept called danger signals. The immune system doesn't just look for foreign molecules. It also looks for signs of cellular distress or damage. When cells are injured, they release certain molecules that signal danger, alerting the immune system that something is wrong. This helps distinguish between harmless foreign substances, like food proteins, and genuinely threatening invaders. The gut presents a special challenge. It's full of foreign organisms, trillions of bacteria that are essential for digestion and health. The immune system has to tolerate these microbes while still being ready to attack pathogens. It does this through a delicate balance of tolerance and vigilance, maintaining a truce with beneficial bacteria while remaining alert for harmful ones. Pregnancy is another unique situation. A fetus is genetically half from the mother and half from the father, making it partially foreign. The immune system should, in theory, attack it, but special mechanisms at the placenta suppress immune activity, creating a protected space where the fetus can develop without being rejected. This is one of the most remarkable examples of immune tolerance in nature. The immune system's ability to distinguish self from foreign is one of the most sophisticated recognition systems in biology. It combines genetic programming, cellular education, molecular markers, and constant surveillance to protect you from threats while sparing your own healthy tissue. It's a system that took millions of years to evolve, and it operates mostly with stunning accuracy. When it works, you stay healthy. When it fails, the consequences remind us just how delicate and essential that balance is. You look at the clouds and see a face. You hear a voice in the sound of wind or static. You notice that every time you think about someone, they call you, and you wonder if it's more than coincidence. Your brain is constantly finding patterns, connections, and meaning in the world around you. But sometimes, you're finding patterns where none exist. This tendency has a name, or rather, two names: pareidolia and apophenia. Pareidolia is the specific tendency to perceive meaningful images, especially faces, in random or ambiguous stimuli. It's why you see a face on the moon, why burnt toast occasionally looks like a religious figure, why shadows and clouds can seem to form recognizable shapes. Apophenia is broader, the general tendency to perceive connections and meaningful patterns in random or unrelated data. It's seeing significance in coincidences, finding hidden messages in unrelated events, or detecting conspiracies in noise. Both phenomena stem from the way your brain processes information. Your brain is not a passive recorder. It's an active interpreter, constantly trying to make sense of incomplete, ambiguous, or noisy input. And one of its most powerful tools for making sense of the world is pattern recognition. Pattern recognition allowed your ancestors to survive. Spotting the outline of a predator in the bushes, recognizing edible plants, detecting social cues in facial expressions. All of these required the ability to identify meaningful patterns quickly. But pattern recognition comes with a trade-off. Your brain can make two types of errors: false negatives, missing a pattern that's actually there, and false positives, seeing a pattern that isn't there. In evolutionary terms, false positives are often less costly than false negatives. If you see a face-like pattern in the bushes and it's not a predator, you've lost nothing but a moment of caution. But if you miss the predator because you didn't detect the pattern, you could die. So your brain evolved to err on the side of caution, to detect patterns even when the evidence is ambiguous, even when the pattern might not be real. This bias is especially strong for faces. Humans are intensely social, and facial recognition is critical for survival and social interaction. Your brain has specialized regions, like the fusiform face area, dedicated to processing faces. These regions are so sensitive that they activate even for face-like patterns that aren't actual faces. Two dots and a line below them. Your brain sees a face. This is why pareidolia most commonly involves faces. Your brain is hypervigilant for them, ready to detect even the suggestion of a face in ambiguous input. The same principle applies to sounds. Your auditory system is tuned to detect voices and meaningful sounds, like footsteps or growls, even in noisy environments. Sometimes this means hearing words or voices in random noise, like static, wind, or machinery. This is called auditory pareidolia, and it's particularly common when you're expecting to hear something or when you're in a heightened state of alertness. Apophenia extends this pattern seeking to abstract connections. Your brain is constantly looking for cause and effect, trying to predict what will happen next based on what happened before. When two events occur close together in time, your brain often assumes they're related, even if they're not. This is the basis for superstitions. You wore a certain shirt and had a good day, so now you believe the shirt is lucky. You avoided cracks in the sidewalk and nothing bad happened, so you continue the behavior, even though there's no causal link. The brain's prediction machinery reinforces these patterns. Once you've detected a pattern, even a false one, your brain starts looking for confirming evidence. This is called confirmation bias. You notice the times the pattern holds and ignore or forget the times it doesn't. Over time, this selective attention strengthens your belief in the pattern, even though it's built on randomness. Pattern seeking also interacts with your emotional state. When you're anxious or stressed, your brain becomes even more prone to detecting patterns, particularly threatening ones. This makes sense from a survival perspective. In dangerous situations, it's better to be hypervigilant, to overinterpret ambiguous signals, than to be relaxed and miss a real threat. But it also means that anxiety can lead to increased pareidolia and apophenia, seeing danger or meaning where there is none. Cultural and social factors play a role too. If your culture emphasizes spiritual or supernatural explanations, you're more likely to interpret ambiguous patterns as signs, omens, or messages from beyond. If your community shares stories of hidden patterns or conspiracies, you're more likely to detect them yourself. Pattern seeking is influenced by what you expect to find, and expectations are shaped by your environment and beliefs. There's also a neurological component. Dopamine, the neurotransmitter associated with reward and motivation, also plays a role in pattern detection. Higher dopamine levels increase your tendency to see patterns, even in random data. This is why certain mental health conditions, like schizophrenia, which involve dysregulated dopamine systems, are associated with heightened apophenia. People with schizophrenia often see connections and meanings that others don't, perceiving hidden messages or conspiracies in everyday events. But pattern seeking isn't inherently pathological. It's a fundamental feature of cognition, essential for learning, creativity, and problem solving. Scientists detect patterns in data. Artists see patterns in form and color. Musicians hear patterns in sound. The difference between healthy pattern recognition and problematic apophenia is whether the patterns you detect are real and useful, or whether they lead you to false beliefs and poor decisions. The challenge is that your brain can't always tell the difference. It's designed to detect patterns, not to verify them. Verification requires additional cognitive work, testing hypotheses, seeking disconfirming evidence, considering alternative explanations. But these processes are slower and more effortful than automatic pattern detection. So your default mode is to see patterns first and question them later, if at all. Pattern seeking is a window into how your brain works, constantly active, constantly interpreting, constantly trying to impose order on a complex and often random world. It's a powerful tool, but like all tools, it can be misused. The faces you see in clouds, the coincidences you notice, the connections you draw, they're all products of a brain doing what it evolved to do: find meaning, even when meaning isn't there. You've been running for 20, maybe 30 minutes. Your legs are tired, your breathing is heavy, but then something shifts. The discomfort fades into the background. You feel lighter, almost euphoric. Your mind clears, worries dissolve, and you're filled with a sense of calm and well-being that seems to come from nowhere. This is the runner's high, and for years people assumed it was all about endorphins. But the reality is more complex and more interesting. Endorphins do play a role. These are your body's natural painkillers, produced by the pituitary gland and the hypothalamus during intense physical activity. Structurally, endorphins are similar to opioids like morphine, and they bind to the same receptors in the brain, reducing pain and creating feelings of pleasure. When you push your body through sustained exercise, endorphin levels rise, and this contributes to the pain relief you feel, allowing you to keep going even when your muscles are fatigued. But here's the problem with the endorphin explanation. Endorphins are large molecules. They don't easily cross the blood-brain barrier, the protective layer that separates circulating blood from brain tissue. Most of the endorphins released during exercise stay in the bloodstream and peripheral nervous system, affecting your body but not necessarily your brain. This raised questions about whether endorphins alone could explain the mental and emotional effects of the runner's high. The answer came from research into a different system, the endocannabinoid system. Endocannabinoids are naturally occurring chemicals in your body that are structurally similar to the active compounds in cannabis. The two main endocannabinoids are anandamide, sometimes called the bliss molecule, and 2-AG. Unlike endorphins, endocannabinoids are small, fat-soluble molecules that easily cross the blood-brain barrier, and during sustained aerobic exercise, their levels increase significantly. Studies have shown that after moderate to intense exercise, blood levels of anandamide rise substantially, and these molecules reach the brain, where they bind to cannabinoid receptors, particularly CB1 receptors. When these receptors are activated, they produce effects remarkably similar to what people report during a runner's high: reduced anxiety, decreased pain perception, feelings of calm, mild euphoria, and an overall sense of well-being. Researchers tested this by giving animals drugs that block cannabinoid receptors. When the receptors were blocked, the animals no longer showed the reduced anxiety and increased pain tolerance that normally follow exercise. But when they blocked opioid receptors, the effects persisted. This suggests that the endocannabinoid system, not endorphins, is the primary driver of the psychological effects we associate with runner's high. The timing matters too. The runner's high typically doesn't kick in immediately. You need to sustain moderate to vigorous aerobic activity for at least 20 to 30 minutes before the effects appear. This delay corresponds to the time it takes for endocannabinoid levels to rise significantly and for these molecules to cross into the brain and activate receptors. It's not an instant switch. It's a gradual buildup that eventually reaches a threshold where you start to feel the shift. There's also a reward system component. Exercise activates the same neural pathways involved in motivation and reward, particularly circuits involving dopamine. When you exercise regularly, your brain learns to associate the activity with the positive feelings that follow, creating a motivation loop. This is why people who exercise consistently often crave it. Their brains have been conditioned to expect the reward, and the endocannabinoid release is a key part of that reward signal. From an evolutionary perspective, this system makes sense. For most of human history, sustained physical activity was necessary for survival: hunting, gathering, migrating long distances. The ability to keep moving, even when tired, could mean the difference between eating and starving, between escaping danger and being caught. A neurochemical reward system that reduces pain and creates positive feelings during sustained exertion would have encouraged our ancestors to keep going, to push through discomfort in pursuit of essential goals. The intensity and type of exercise matter. The runner's high is most commonly associated with aerobic activities: running, cycling, swimming, anything that gets your heart rate up and keeps it there for an extended period. High-intensity interval training can trigger it, but so can moderate, steady-state cardio. The key is sustained effort. Activities that are too brief or too intermittent don't give the system enough time to ramp up. Individual variation is significant. Not everyone experiences the runner's high, and among those who do, the intensity varies. Factors like genetics, fitness level, exercise history, and even mood before starting can all influence whether and how strongly the effect occurs. People who exercise regularly often report more consistent and pronounced highs, possibly because their endocannabinoid systems are more responsive or because their brains are more sensitized to the reward. Stress levels also play a role. Exercise is a form of physical stress, but it's controlled and temporary. The body's response to this manageable stress includes not just endocannabinoid release, but also changes in cortisol levels, improved circulation, and enhanced mood-regulating neurotransmitter function. When these systems work together, the result is a powerful shift in both physical and mental state. Interestingly, the runner's high shares features with meditation and other mindfulness practices. Both involve sustained, rhythmic activity, whether physical or mental, and both can lead to altered states of consciousness characterized by reduced anxiety, increased present moment awareness, and feelings of euphoria or transcendence. The overlap suggests that the brain has multiple pathways to similar states, and sustained physical movement is one of the most accessible. The runner's high isn't just a pleasant side effect. It's a sophisticated reward system that encourages behavior essential for health and survival. It's your brain and body working together to say, keep going. This is good for you. And while the subjective experience can feel almost mystical, the mechanisms are grounded in neurochemistry, evolution, and the remarkable adaptability of the human body under sustained physical demand. You skip breakfast, and by mid-morning your stomach is growling. You feel hungry, irritable, maybe a little lightheaded. The obvious explanation is that your stomach is empty, signaling your brain that it's time to eat. But hunger is far more complex than an empty stomach. It's a sophisticated signaling system involving hormones, blood sugar levels, and intricate feedback loops in the brain. Understanding how hunger really works reveals just how tightly your body monitors and regulates energy balance. The process begins with two key hormones, ghrelin and leptin. Ghrelin is often called the hunger hormone. It's produced primarily in the stomach, and its levels rise when your stomach is empty. When ghrelin reaches the brain, specifically the hypothalamus, a small but crucial region that regulates appetite and metabolism, it signals that energy stores are low and you need to eat. Ghrelin levels peak right before meals and drop shortly after you eat, creating the familiar cycle of hunger and satiation. Leptin works in the opposite direction. It's produced by fat cells, and its job is to signal long-term energy stores. When your fat reserves are adequate, leptin levels are higher, and the signal to the hypothalamus is, we have enough energy. You don't need to eat as much. When fat stores are low, leptin levels drop, and the brain interprets this as a signal to increase appetite and conserve energy. Leptin is essentially your body's fuel gauge, providing information about overall energy reserves rather than immediate need. But hunger isn't just about these two hormones. Blood sugar, or glucose, plays a critical role. Your brain relies almost exclusively on glucose for energy, and it monitors blood sugar levels constantly. When glucose drops, sensors in the hypothalamus and in the liver detect the change and trigger hunger signals. This is why you might feel suddenly weak or shaky if you haven't eaten in a while. Your brain is alerting you that its primary fuel source is running low. Insulin, the hormone that regulates blood sugar, is also involved. After you eat, especially if you eat carbohydrates, your blood sugar rises. The pancreas releases insulin to help cells absorb glucose from the bloodstream. Insulin levels signal to the brain that food has been consumed and energy is available, contributing to the feeling of satiety. But if you eat foods that cause rapid spikes in blood sugar followed by rapid drops, like sugary snacks, you can end up feeling hungry again soon after, even though you technically consumed calories. This is because the quick insulin response brings blood sugar down sharply, triggering hunger signals even though energy was recently available. The hypothalamus is the control center for all of this. It has specific populations of neurons that respond to ghrelin, leptin, insulin, and glucose. Some neurons, called NPY-AG-RP neurons, are activated by hunger signals and drive food-seeking behavior. Others, called POMC neurons, are activated by satiety signals and suppress appetite. The balance between these two populations determines whether you feel hungry or full at any given moment. There's also a stretch receptor component. Your stomach does send signals based on physical distension. When your stomach stretches as it fills with food, mechanoreceptors in the stomach wall detect this and send signals via the vagus nerve to the brain, contributing to the feeling of fullness. This is why eating high-volume, low-calorie foods like vegetables can make you feel full even though they provide relatively little energy. The physical sensation of a full stomach is part of the equation, even if it's not the whole story. The type of food you eat influences hunger too. Protein is particularly effective at promoting satiety because it triggers the release of several gut hormones, including peptide YY and GLP-1, which signal fullness to the brain. Fat also promotes satiety, though through different mechanisms, partly by slowing gastric emptying, meaning food stays in your stomach longer. Carbohydrates, especially simple sugars, are less effective at creating lasting satiety, which is why a sugary snack might leave you hungry again within an hour. Leptin resistance is a significant problem in obesity. In theory, people with more fat should have higher leptin levels and feel less hungry. But in obesity, the brain often becomes resistant to leptin's signal, similar to how cells can become resistant to insulin in diabetes. The leptin is there, but the brain doesn't respond to it effectively. The result is persistent hunger and difficulty feeling satisfied, even when energy stores are more than adequate. This resistance makes weight loss challenging because the brain continues to signal that the body needs more food, even when it doesn't. Sleep deprivation affects hunger regulation dramatically. When you don't get enough sleep, ghrelin levels rise and leptin levels fall, creating a hormonal environment that increases hunger and decreases satiety. This is why people who are sleep-deprived often feel hungrier and crave high-calorie foods. The brain is perceiving an energy deficit, partly because lack of sleep is itself metabolically demanding, and it's trying to compensate by increasing food intake. Stress also influences hunger, though the effect varies. Acute stress often suppresses appetite by activating the sympathetic nervous system and releasing hormones like cortisol and adrenaline. But chronic stress can have the opposite effect. Elevated cortisol levels over time can increase appetite, particularly for high-calorie, palatable foods. This is often called stress eating, and it's driven by the brain's attempt to cope with ongoing stress by seeking comfort through food. There's even a social and psychological component. Hunger isn't purely physiological. Your environment, habits, and emotions all influence when and how much you eat. Seeing or smelling food can trigger hunger, even if your body doesn't need energy. Eating at regular times trains your body to expect food at those times, creating anticipatory hunger. Emotional states like boredom, sadness, or anxiety can also trigger eating behavior, sometimes overriding the body's actual energy needs. Hunger is a complex, multi-layered system that integrates information from your stomach, your fat stores, your blood, and your brain. It's not just about an empty stomach or a simple on-off switch. It's a finely tuned regulatory network that balances immediate energy needs with long-term reserves, influenced by hormones, metabolism, sleep, stress, and even learned behavior. Understanding this complexity helps explain why managing hunger and appetite isn't as simple as willpower, and why eating patterns, food choices, and lifestyle factors all play critical roles in how hungry you feel and how your body regulates energy. You hear a song that was popular when you were 16, and suddenly you're transported. The memories flood back, where you were, who you were with, how you felt. Music from your teenage years and early 20s often holds a special place in your emotional life, more powerful and evocative than music from other periods. This isn't just nostalgia. There's a psychological and neurological reason why the music from this specific time in your life feels uniquely meaningful. It's called the reminiscence bump. The reminiscence bump refers to the tendency for people to have stronger, more vivid memories from adolescence and early adulthood, roughly ages 12 to 25, than from other periods of life. When older adults are asked to recall significant life events or memories, a disproportionate number come from this window. It's not that nothing important happens in childhood or later adulthood. It's that the teenage years and early 20s are a period of heightened encoding, when experiences are processed more deeply and stored more permanently. Several factors contribute to this. First, adolescence and early adulthood are periods of intense identity formation. You're figuring out who you are, separate from your parents, exploring values, beliefs, interests, and relationships. Music is often central to this process. The music you listen to during these years becomes part of how you define yourself and how you connect with peers. It's not just background noise. It's a soundtrack to your emerging identity. Because identity formation is such a critical developmental task, the experiences associated with it, including the music you listen to, are encoded with extra emotional weight. The brain tags these memories as important, ensuring they're stored deeply and remain accessible throughout life. This is why you can often remember the lyrics to songs from your teenage years decades later, even if you haven't heard them in years, while songs you heard last month might already be forgotten. Second, this period of life is full of firsts. First love, first heartbreak, first time living away from home, first job, first sense of real independence. These novel experiences create strong memories because novelty itself enhances encoding. When something is new, your brain pays more attention, processes the experience more thoroughly, and stores it more durably. Music that accompanies these firsts gets woven into the memory, becoming inseparable from the experience. There's also a neurobiological component. The teenage brain is in a state of heightened plasticity, particularly in areas involved in emotion and memory. The prefrontal cortex, which handles planning and decision-making, is still developing, while the limbic system, which processes emotion, is highly active. This creates a period where emotional experiences are felt intensely and encoded deeply. Music, which is inherently emotional, benefits from this heightened emotional processing. The reminiscence bump also reflects a period of relative stability in autobiographical memory. Childhood memories are often fragmented or unreliable because the hippocampus and other memory systems are still maturing. Later in life, as routines become more established and fewer genuinely novel experiences occur, fewer strong memories are formed. But during adolescence and early adulthood, the memory systems are fully functional, and life is filled with change and novelty, creating ideal conditions for lasting memory formation. Cultural factors matter too. Adolescence is when many people become most engaged with popular culture. Music is a central part of social life, shared experiences at concerts, parties, or simply listening with friends. The social context amplifies the emotional significance of the music. It's not just about the song itself. It's about belonging, connection, and shared identity. These social dimensions make the music more memorable because they tie it to relationships and group experiences, both of which are powerful memory enhancers. There's also a phenomenon called the mere exposure effect, where repeated exposure to something increases your liking for it. During your teenage years, you might listen to the same songs or albums obsessively, far more than you would as an adult with a broader musical history and more competing demands on your time. This repeated exposure creates strong associations and preferences that endure. The emotional intensity of adolescence plays a role as well. Emotions during this period often feel more extreme. Happiness is euphoric. Sadness is devastating. Everything feels heightened. Music that captures or accompanies these intense emotions becomes linked to them in memory. When you hear the song again years later, it doesn't just remind you of the time. It can actually recreate some of the emotional state you were in, a phenomenon called state-dependent memory. Interestingly, the reminiscence bump isn't unique to music. It applies to all kinds of memories. But music is particularly effective at triggering these memories because of how it's processed in the brain. Music engages multiple systems simultaneously: auditory processing, emotional response, motor areas involved in rhythm and memory. This multi-system activation creates rich, multi-dimensional memories that are easier to retrieve and more emotionally powerful when they resurface. As people age, they often return to the music of their youth, especially during times of stress or transition. This isn't just about nostalgia or resistance to change. It's about accessing a period of life when identity was being actively formed, when possibilities felt limitless, and when emotional experiences were at their most intense. The music from that time carries echoes of who you were becoming, and reconnecting with it can feel like reconnecting with a version of yourself that still matters. The reminiscence bump explains why generation-defining songs and artists emerge during this period. The music that defines a generation is often the music that was popular when that generation was in their teens and early 20s. It's not that older or younger people don't enjoy music. It's that the music encountered during this critical window becomes permanently embedded in identity and memory in a way that later music rarely does. You hear a joke and you laugh. But why? What's happening in your brain that turns a string of words or an unexpected situation into a physical response that involves your face, your breath, your whole body? Laughter seems simple, automatic, but the psychology and neuroscience behind it reveal a sophisticated system that's deeply tied to how we think, process information, and connect with others. One of the oldest and most influential theories of humor is incongruity theory. The basic idea is that we laugh when we perceive something that violates our expectations in a surprising but ultimately harmless way. Your brain is constantly making predictions about what will happen next, and humor often works by setting up an expectation and then subverting it. The setup leads you in one direction. The punchline goes somewhere else. The mental twist creates a moment of incongruity, and if it's done well, you laugh. This explains why jokes often have a specific structure. The setup establishes a context and creates an expectation. The punchline delivers information that's incompatible with that expectation, forcing your brain to reinterpret what came before. The surprise, combined with the resolution of the incongruity, triggers laughter, but the incongruity can't be too extreme. If the punchline is completely nonsensical or threatening, the response isn't laughter, it's confusion or fear. The key is that the violation has to be benign. This leads to the benign violation theory, a more recent framework that builds on incongruity. According to this theory, humor occurs when something seems wrong, threatening, or unsettling, a violation but simultaneously okay, acceptable, or safe, benign. The tension between these two perceptions creates humor. If something is purely benign, it's not funny, it's just pleasant. If it's purely a violation, it's not funny, it's disturbing. But when both conditions are met, when something feels wrong yet safe, the result is laughter. This explains why humor is so context-dependent. A joke that's funny in one setting might be offensive in another. Whether something feels benign depends on your relationship with the person telling the joke, your cultural background, your current emotional state, and the social context. What's benign to you might be a genuine threat to someone else, which is why humor is so personal and why comedy can be controversial. There's also a social dimension. Laughter is fundamentally social. You're about 30 times more likely to laugh in the presence of others than when you're alone. Even when you're watching something funny by yourself, you're more likely to laugh if you can hear or imagine others laughing. This is because laughter evolved not primarily as a response to humor, but as a social bonding mechanism. In evolutionary terms, laughter likely predates language. Primates laugh, though it sounds different from human laughter. It emerges during play, particularly rough and tumble play, as a signal that says, "This is fun. We're not really fighting." Laughter creates and reinforces social bonds, signaling trust, cooperation, and shared understanding. When you laugh with someone, you're synchronizing emotionally and physiologically, which strengthens the connection between you. This is why shared laughter feels so good. It's not just about the joke. It's about the mutual recognition, the shared perspective, the sense of being on the same wavelength with someone else. Laughter releases endorphins and activates reward pathways in the brain, creating feelings of pleasure and bonding. It also reduces stress hormones like cortisol, which is why laughter is often described as therapeutic. The brain regions involved in laughter are widespread. When you process humor, several areas light up. The prefrontal cortex, which handles cognitive processing and expectation, the temporal lobe, which processes language and recognizes incongruity, the amygdala, which assesses emotional significance, and the motor cortex, which generates the physical act of laughing. Dopamine pathways are also activated, which is why laughter feels rewarding. Different types of humor engage different cognitive processes. Puns and wordplay require linguistic processing and the ability to hold multiple meanings simultaneously. Physical comedy, like slapstick, relies on visual processing and empathy. You laugh because you can imagine what it feels like to trip or get hit with a pie, but you know it's not real. Dark humor requires the ability to distance yourself emotionally from disturbing content, finding the incongruity in tragedy or taboo. Not everyone finds the same things funny, and this reveals something about individual differences in cognition and temperament. People with higher tolerance for ambiguity and complexity often enjoy more sophisticated or absurdist humor. People who are more conscientious might prefer cleaner, more structured jokes. Personality, intelligence, and even mood all influence what you find funny at any given moment. Laughter also serves a regulatory function. It can diffuse tension in uncomfortable situations, signal that a threat isn't serious, or provide relief after a stressful moment. This is why people sometimes laugh nervously or at inappropriate times. The laughter isn't about finding something funny. It's about managing emotion or social discomfort. There's also contagious laughter, where hearing someone laugh makes you laugh, even if you don't know what's funny. This is driven by mirror neurons and social mimicry. Your brain automatically simulates the emotional state of people around you, and laughter is one of the most contagious behaviors. This is why laugh tracks work, even though logically you know they're artificial. The sound of laughter primes your brain to find something funny. Humor and laughter are complex, multi-layered phenomena that blend cognition, emotion, and social behavior. They require the ability to process information rapidly, detect incongruity, assess threat levels, and connect with others. They're uniquely human in their sophistication, though their roots go deep into our evolutionary past. And they serve purposes far beyond entertainment, bonding groups, reducing stress, navigating social hierarchies, and making sense of a complicated world by finding the absurdity in it. You spend about a third of your life asleep, and for most of that time it seems like your body is simply resting, recharging for the next day. But while you're unconscious, your brain is far from idle. One of the most important things happening during sleep is a cleaning process, a system that removes metabolic waste and toxins that accumulate during waking hours. This process is critical for brain health, and it only happens efficiently when you're asleep. It's called the glymphatic system. The glymphatic system is the brain's waste clearance mechanism, discovered relatively recently in 2012. The name is a combination of glia, referring to glial cells, and lymphatic, referring to the body's lymphatic system, which removes waste from other tissues. The brain doesn't have a traditional lymphatic system. Instead, it has this specialized glymphatic system that uses cerebrospinal fluid, CSF, to flush out waste. Here's how it works. During the day, as your brain cells are active, they produce metabolic byproducts. One of the most concerning is beta amyloid, a protein fragment that, in high concentrations, is associated with Alzheimer's disease. Other waste products include tau proteins, lactate, and various metabolic debris. These substances build up in the spaces between cells, and if they're not cleared, they can interfere with neuronal function and contribute to neurodegeneration. During sleep, particularly during deep non-REM sleep, something remarkable happens. The brain's glial cells, specifically astrocytes, shrink. This shrinkage increases the size of the spaces between brain cells, the interstitial space, by as much as 60%. With more space available, cerebrospinal fluid can flow more freely through the brain tissue. Cerebrospinal fluid is produced continuously in the brain's ventricles, the hollow spaces deep within the brain. Normally, CSF circulates around the brain and spinal cord, providing cushioning and support. But in the glymphatic system, CSF is pushed along pathways that run alongside blood vessels, called perivascular spaces. These spaces act like pipes, directing CSF deep into the brain tissue. As CSF flows through the interstitial spaces, it picks up waste products. The fluid, now carrying metabolic debris, drains out of the brain along venous pathways and eventually into the lymphatic vessels in the neck, where the waste is processed and eliminated from the body. This convective flow, the bulk movement of fluid carrying dissolved substances, is far more efficient than simple diffusion for clearing large molecules like beta amyloid. The system is most active during sleep. Studies using imaging techniques have shown that the glymphatic flow increases dramatically when animals and humans are asleep compared to when they're awake. The rate of waste clearance can be twice as high during sleep. This is partly because the increase in interstitial space during sleep allows for more efficient fluid movement, and partly because certain brain states associated with sleep, particularly slow-wave sleep, facilitate the pulsatile flow of CSF. The pulsations of arterial blood vessels also help drive CSF movement. Each heartbeat creates a pressure wave that pushes CSF through the perivascular spaces. During sleep, these pulsations are more effective because the brain is in a more receptive state for fluid exchange. The coordination between cardiovascular rhythms and brain state creates optimal conditions for waste removal. Beta amyloid clearance is especially important. During waking hours, beta amyloid accumulates as a normal byproduct of neuronal activity. If it's cleared efficiently each night, it doesn't reach harmful levels. But if sleep is disrupted or insufficient, the clearance process is impaired. Over time, beta amyloid can aggregate into plaques, a hallmark of Alzheimer's disease. This connection between sleep, glymphatic function, and Alzheimer's is one of the reasons why chronic sleep deprivation is considered a risk factor for neurodegenerative diseases. Sleep position might even matter. Some research suggests that sleeping on your side is more effective for glymphatic clearance than sleeping on your back or stomach, though this is still being studied. The idea is that certain positions allow for better CSF flow through the brain, optimizing the cleaning process. Age affects the glymphatic system. As people get older, the system becomes less efficient. Glial cells don't shrink as much during sleep, reducing the space available for CSF flow. Blood vessel pulsations weaken. The result is that older adults clear waste less effectively, which might contribute to the increased risk of neurodegenerative diseases with age. Maintaining good sleep quality becomes even more important as the system's natural efficiency declines. Other factors influence glymphatic function too. Alcohol impairs it, reducing the brain's ability to clear waste even if you're technically asleep. Exercise enhances it, possibly by improving cardiovascular function and increasing CSF production. Chronic stress and inflammation can disrupt it, as can certain medical conditions that affect sleep quality or vascular health. The discovery of the glymphatic system has profound implications for understanding why sleep is essential. It's not just about consolidating memories or restoring energy. It's about maintaining a clean, functional brain. Every night you sleep, you're giving your brain the opportunity to remove the metabolic waste that accumulated during the day. Skip sleep, and that waste remains, accumulating over time and potentially contributing to cognitive decline. This also helps explain why sleep deprivation has such immediate effects on cognitive function. When you don't sleep enough, your brain is operating with elevated levels of metabolic waste. Neural communication becomes less efficient. Attention, memory, and decision-making all suffer. It's not just that you're tired. It's that your brain is literally cluttered with debris that should have been cleared during sleep. The glymphatic system is a powerful reminder that sleep is active and restorative, not passive and wasteful. While you rest, your brain is hard at work, flushing out toxins, repairing damage, and preparing for another day of activity. It's a cleaning crew that only comes out at night, and it's essential for keeping your brain healthy throughout your life. Have you ever noticed yourself crossing your arms right after someone else does? Or leaning forward in conversation exactly when your friend leans toward you? It happens without thinking, almost like a dance you never learned but somehow know the steps to. This automatic copying of other people's gestures, expressions, and postures has a name. It's called the chameleon effect. The chameleon effect is our unconscious tendency to mimic the body language, speech patterns, and behaviors of the people around us. Just like a chameleon changes its colors to blend into its environment, we subtly adjust our physical presence to match those we're interacting with. And here's the fascinating part. We almost never realize we're doing it. Research into this phenomenon began in earnest in the late 1990s when psychologists noticed that people naturally synchronize their movements during conversations. If one person touched their face, the other might do the same moments later. If someone spoke slowly and calmly, their conversation partner often matched that rhythm. This wasn't conscious imitation. It was happening at a level below awareness, driven by parts of the brain designed for social connection. But why do we do this? The answer lies deep in our evolutionary history. Humans are social creatures. For most of our existence, survival depended on cooperation, trust, and group cohesion. Being able to connect quickly with others, to signal that you're friendly and safe, meant the difference between being welcomed into a community or being cast out. Mimicry became one of nature's shortcuts for building rapport. When we mirror someone's body language, we're sending an unconscious signal. We're saying, without words, that we understand them, that we're on the same wavelength. Studies have shown that people who are being mimicked tend to like the person doing the mimicking more, even when they don't consciously notice what's happening. They feel more comfortable, more trusting, and more connected. The simple act of copying a posture or gesture creates a sense of harmony between two people. There's also a neurological component at play here. Scientists have discovered something called mirror neurons, specialized brain cells that activate both when we perform an action and when we observe someone else performing that same action. If you watch someone smile, the mirror neurons associated with smiling light up in your own brain, almost as if you're smiling too. This neural mirroring creates a kind of shared experience, a bridge between minds that helps us understand what others are feeling and thinking. The chameleon effect doesn't just happen in pleasant situations either. It's been observed across cultures and contexts. Strangers meeting for the first time, colleagues in a meeting, friends catching up over coffee. The more engaged people are in an interaction, the more likely they are to synchronize their movements. It's as if our bodies are constantly negotiating connection, testing the waters of rapport through subtle physical echoes. Interestingly, not everyone mirrors to the same degree. People who are naturally empathetic or socially attuned tend to exhibit stronger mimicry. Those who score high on measures of perspective-taking and emotional sensitivity are more likely to unconsciously adopt the postures and expressions of others. On the flip side, individuals with certain social difficulties, such as those on the autism spectrum, may show reduced mirroring behavior, which can affect how smoothly social interactions unfold. Understanding the chameleon effect also has practical implications. In negotiations, job interviews, or first dates, being aware of body language can help build connection. Leaning in when someone leans in, nodding when they nod, matching their energy level, these small adjustments can create an atmosphere of trust and openness. But it's important that this remains natural. Forced or exaggerated mimicry can feel manipulative or insincere. At its core, the chameleon effect reveals something beautiful about human nature. We are wired for connection. Our brains and bodies are designed to sync up with others, to find common ground, and to build bridges through the simplest of gestures. Every time we unconsciously mirror someone, we're participating in an ancient dance of belonging, one that's been happening for as long as humans have gathered together. You're standing at the edge of a cliff, a tall building, or even just a high balcony. The view is breathtaking, the air is clear. And then out of nowhere, a strange thought crosses your mind. What if I jumped? It's not that you want to, you're not suicidal, you have no intention of doing it. But the thought appears anyway, sudden and uninvited, like a whisper from some hidden corner of your mind. If you've ever experienced this, you're not alone. This phenomenon has a name. The French call it l'appel du vide, the call of the void. L'appel du vide, or the high place phenomenon as psychologists call it, is surprisingly common. Studies suggest that around half of all people have experienced it at some point. It's that fleeting, intrusive thought that surfaces when you're near a high edge, a moment where your mind imagines the possibility of falling or jumping, even though you have absolutely no desire to follow through. It's unsettling, confusing, and for many people, deeply disturbing. Why would the brain generate such a thought? For a long time, this phenomenon was misunderstood. Some believed it was a hidden suicidal impulse, a dark urge lurking beneath the surface. But research has shown that's not the case at all. In fact, people who experience the call of the void are often the ones least likely to actually harm themselves. The thought isn't a desire, it's something else entirely. One explanation involves the way our brain processes danger. When you stand near a precipice, your survival instincts kick in immediately. Your body tenses. Your heart rate might increase slightly. You take a step back without thinking. This is your brain's automatic safety system at work, designed to keep you alive. But here's where it gets interesting. Sometimes, the brain's alarm system fires so quickly that the conscious mind hasn't quite caught up yet. You feel the pull to step back, but you don't immediately understand why. Your conscious mind searches for an explanation and lands on the most dramatic possibility. Did I almost jump? Was I about to fall? In other words, the intrusive thought might be a misinterpretation of your own safety response. Your brain protected you from danger, and in the split second of confusion that followed, your mind generated a frightening narrative to explain the sudden jolt of fear. It's not a call to jump. It's a recognition of the danger you just instinctively avoided. There's also a connection between the high place phenomenon and anxiety. People who experience higher levels of general anxiety are more likely to report these intrusive thoughts. This makes sense when you consider how anxiety works. Anxious brains are constantly scanning for threats, always on alert, always preparing for the worst-case scenario. When you're standing somewhere high, an anxious mind doesn't just register the height. It runs through every possible danger, including the most extreme ones. What if I fell? What if I lost control? What if something went wrong? These thoughts aren't plans. They're not wishes. They're the mind's way of testing boundaries, of running simulations to make sure you stay safe. Psychologists sometimes refer to these as intrusive thoughts, unwanted mental images or ideas that pop up without permission. They can be about anything, heights, harm, taboo actions, and they're a normal part of how the human brain functions, especially under stress. It's also worth noting that the call of the void can be strangely fascinating. There's something about the edge, the boundary between safety and danger, that draws our attention. Humans are curious creatures. We're drawn to limits, to the edges of experience. Standing on a cliff offers a visceral reminder of our own fragility, of how thin the line is between life and death. That awareness can be uncomfortable, but it can also be profound. Understanding l'appel du vide can bring relief. For many people, the intrusive thought itself becomes a source of worry. They wonder if something is wrong with them, if the thought means something darker. But recognizing it as a common psychological quirk, a misfiring of the brain's safety system, or an anxious mind running through scenarios, can take away much of its power. The thought doesn't define you. It's just noise, a momentary glitch in the complex machinery of consciousness. So the next time you're standing somewhere high and that strange thought crosses your mind, remember this. It's not a call to action. It's not a hidden desire. It's just your brain doing what it does best, keeping you safe, sometimes in ways that feel confusing or strange. You're not broken. You're human. And that fleeting whisper from the void, it's just a reminder of how much your mind wants to keep you here, alive and firmly on solid ground. Think about who you were 10 years ago. Maybe you were more impulsive, more cautious, more outgoing, or more reserved. Now think about who you are today. Chances are you're not exactly the same person. You've grown, learned, adapted. Yet at the same time, there's something about you that feels continuous, a core sense of self that's remained steady through all those years. This paradox, how personality can be both stable and changing, is one of the most fascinating puzzles in psychology. For a long time, psychologists debated whether personality was fixed or flexible. Some argued that by the time you reach adulthood, your personality is essentially set, like wet clay that's been fired in a kiln. Others believed personality was fluid, constantly shaped and reshaped by experience. The truth, as it turns out, lies somewhere in between. Personality does have a stable foundation, but it's not rigid. It evolves slowly and subtly throughout your life. This is where the concept of set point theory comes in. In psychology, set point theory originally referred to things like body weight or happiness, the idea that people tend to return to a baseline level despite temporary changes. The same principle applies to personality. Each of us has a kind of personality set point, a natural baseline shaped by genetics, early childhood experiences, and brain structure. If you're naturally introverted, for example, that tendency is likely to persist. You might become more comfortable in social situations over time, but you probably won't transform into the life of the party. Research supports this stability. Studies that follow people over decades show that the big five personality traits, openness, conscientiousness, extroversion, agreeableness, and neuroticism, remain fairly consistent, especially after age 30. If you score high on conscientiousness in your 20s, you'll likely still be organized and reliable in your 50s. That core structure doesn't vanish. It's the foundation you build your life on. But here's where it gets interesting. While the foundation stays put, the structure on top of it can shift. Personality isn't just a set of fixed traits. It's also a dynamic system that responds to life. Major experiences, relationships, careers, trauma, parenthood, loss can leave lasting imprints. These don't erase your baseline personality, but they do adjust it, like fine-tuning an instrument. Psychologists call this process life experience integration. As you move through life, you accumulate experiences that challenge, reinforce, or reshape how you see yourself and how you interact with the world. If you go through a difficult period that requires resilience, you might develop a stronger sense of emotional stability. If you enter a career that demands social interaction, you might become more extroverted over time. These changes don't contradict your set point. They build on it, adding layers of complexity and nuance. There's also the concept of trait stability versus adaptation. Stability refers to the consistency of your core traits, the parts of you that remain recognizable over time. Adaptation, on the other hand, is your ability to adjust your behavior to fit different contexts and roles. You might be naturally introverted, but you learn to be more outgoing in professional settings because the situation demands it. That's not a change in your core personality. It's behavioral flexibility, a skill you've developed. The balance between stability and change is influenced by several factors. Age plays a role. Personality tends to become more stable as we get older, partly because we settle into routines and environments that match our natural tendencies. But younger people often show more variability, experimenting with different identities and roles as they figure out who they are. Culture matters too. In individualistic societies, people are encouraged to express and develop their unique traits. In collectivist cultures, there's more emphasis on adapting to social norms and group harmony. This doesn't mean personality is entirely culturally determined, but it does shape how much flexibility people feel they have. Then there's intentional change. Unlike physical set points, personality isn't entirely out of your control. People can and do work on themselves. Therapy, mindfulness, deliberate practice, these can all shift aspects of personality over time. If you're naturally anxious, for example, you can develop coping strategies that reduce the intensity of that trait. You might never become a completely carefree person, but you can move the needle. What makes this especially fascinating is that both sides are true. You are who you are. There's a continuity to your identity that threads through your entire life. But you're also constantly becoming. Every experience, every choice, every challenge adds something new, refining and reshaping the person you're growing into. In the end, personality isn't a fixed thing or a blank slate. It's both. It's a foundation that stays solid while the building above it grows, changes, and adapts. Understanding this balance can be liberating. You don't have to feel trapped by your nature, but you also don't have to fight against it. You can honor who you are while still leaving room for who you're becoming. Say the word road out loud. Now say it again, and again, and again. Keep going for about 30 seconds. Road, 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 road. Something strange starts to happen. The word begins to feel foreign, disconnected from its meaning. It stops sounding like a word at all and becomes just a collection of sounds, a meaningless noise. If you've ever experienced this, you've encountered a curious psychological phenomenon called semantic satiation. Semantic satiation is the temporary loss of meaning that happens when a word or phrase is repeated over and over in a short period of time. The term was coined by psychologist Leon Jakubowicz James in 1962, though people had noticed the effect long before it had a formal name. It's one of those strange quirks of the mind that makes you realize just how complex and fragile language processing really is. At first, it might seem like a minor oddity, a party trick, or a weird thing that happens when you're bored. But semantic satiation actually reveals something important about how the brain handles language. Words aren't just sounds. They're symbols, mental shortcuts that connect a pattern of noise or letters to a concept, an image, a feeling. When you hear the word road, your brain doesn't just register the sound. It instantly pulls up everything associated with that word: pavement, travel, direction, cars. That entire network of meaning activates in a fraction of a second. But here's the problem. The brain's language system isn't built to process the same input repeatedly without a break. When you say or hear a word over and over, the neurons responsible for recognizing and processing that word start to fatigue. This is a process called neural adaptation. Neurons are incredibly efficient, but they also get tired. When they're activated continuously without variation, their response weakens. The signal gets quieter. The connection between the sound and the meaning starts to fuzz out. Think of it like staring at a bright color for too long. Eventually, the color seems to fade, not because the color has changed, but because your visual neurons have adapted to the stimulus. The same thing happens with words. The meaning doesn't actually disappear. Your brain just temporarily stops responding to it with the same intensity. This phenomenon also involves something called temporary desensitization of word recognition pathways. Every time you encounter a word, your brain follows a specific pathway to decode it, matching the sounds or letters to stored linguistic information. But when that pathway is overused in a short span of time, it becomes less responsive. It's as if the road from sound to meaning gets worn down, and the signal has trouble getting through clearly. Semantic satiation doesn't last long. Usually, the effect fades within a minute or two once you stop repeating the word. The neurons recover, the pathways reset, and the word regains its meaning. But in that brief window, it offers a glimpse into how dependent we are on the seamless functioning of language systems. We take for granted that words have meaning, that they instantly connect us to ideas and concepts. Semantic satiation disrupts that automatic process and reminds us how much mental work is happening beneath the surface. The experience of semantic satiation can also be surprisingly disorienting. Language is one of the primary ways we make sense of the world. When words lose their meaning, even temporarily, it creates a small rupture in that sense-making process. The word becomes strange, alien, almost unsettling. It's a reminder that language, for all its power, is just a construct, a shared agreement about what sounds and symbols mean. Interestingly, semantic satiation doesn't affect everyone equally. Some people experience it more intensely than others. Factors like attention, language proficiency, and even mood can influence how quickly the effect sets in. People who are highly focused on the word seem to reach satiation faster, while those who are distracted or less engaged might not notice it at all. There's also variation across languages. In languages with more complex phonetic structures or tonal systems, semantic satiation might unfold differently. But the core mechanism, neural adaptation and the temporary breakdown of the sound-meaning connection, seems to be universal. Semantic satiation isn't just a curiosity. It's been studied in the context of learning, memory, and even therapy. For example, some researchers have explored whether repeating a fear-related word over and over can reduce its emotional impact, a kind of linguistic desensitization. The results are mixed, but the idea shows how this odd little phenomenon might have practical applications. What semantic satiation really highlights is the delicate balance of the brain's language system. We rely on words to communicate, to think, to understand ourselves and others. But that system isn't unbreakable. It can be disrupted, temporarily short-circuited, by something as simple as repetition. And in those moments when a word loses its meaning, we're reminded of the invisible machinery that makes meaning possible in the first place. Language is a tool, a powerful one, but it's also fragile, held together by neurons that need rest, pathways that need variety, and a brain that's doing its best to keep the whole system running smoothly. Look at a chimpanzee, a gorilla, or a bonobo, and you'll see something familiar. They use tools. They communicate. They care for their young, form social bonds, and even display what looks like empathy. We share about 98% of our DNA with chimpanzees. So what makes us human? What separates us from our closest relatives in the animal kingdom? The answer isn't simple, but it comes down to a few key differences, subtle yet profound, that have allowed humans to build civilizations, create art, and ponder our own existence. One of the most important distinctions is something called theory of mind. Theory of mind is the ability to understand that other individuals have their own thoughts, beliefs, intentions, and perspectives that are different from your own. It's what allows you to recognize that someone else can be mistaken, that they can know something you don't, or that they might be pretending or lying. Humans develop a robust theory of mind early in childhood, usually around age 4 or 5. We can think about what someone else is thinking, and we can even think about what they think we're thinking. This recursive ability, thinking about thinking, is extremely sophisticated. While some primates show signs of basic perspective taking, like understanding what another animal can or cannot see, they don't demonstrate the same depth of mental reasoning that humans do. This capacity has massive implications. Theory of mind is the foundation of empathy, cooperation, teaching, and deception. It allows us to navigate complex social worlds, to predict behavior, to negotiate, and to build cultures based on shared understanding. Without it, human society as we know it wouldn't exist. Then there's language. All primates communicate. They use vocalizations, gestures, facial expressions. But human language is something different entirely. It's recursive. Recursion in language means we can embed ideas within ideas, creating infinite layers of meaning. We can say, "I think that you believe that she hopes will arrive on time." That sentence contains multiple levels of thought, stacked inside each other like nesting dolls. Recursive language gives humans an almost limitless ability to express complex, abstract, and hypothetical ideas. We can talk about the past, imagine the future, describe things that don't exist, and build entire conceptual worlds through words. No other primate has demonstrated this capability. Some apes have been taught sign language and can use symbols to communicate, but they don't generate recursive structures. Their communication is functional and concrete, but it lacks the generative flexibility of human language. Language isn't just about communication. It's a tool for thinking. It allows us to collaborate on a scale unmatched in the animal kingdom. We can share knowledge across generations, preserve information, and coordinate actions with people we've never even met. Language is the scaffold on which culture, science, and philosophy are built. Another key difference is neoteny, specifically the extended period of neoteny that humans experience. Neoteny refers to the retention of juvenile characteristics into adulthood and, more broadly, to the prolonged developmental period. Human children take an extraordinarily long time to mature compared to other primates. While a chimpanzee reaches independence relatively quickly, humans remain dependent on caregivers for years, sometimes well into their teens. This extended childhood isn't a weakness, it's an advantage. During this long developmental window, the human brain remains highly plastic, capable of learning, adapting, and absorbing enormous amounts of information. We don't just inherit instincts. We learn culture, language, skills, social norms, and complex behaviors from the people around us. This extended learning period allows for a level of cultural transmission and innovation that other primates simply don't achieve. Neoteny also affects our physical development. Humans retain certain juvenile features into adulthood, like flatter faces, larger foreheads, and smaller jaws. Some researchers believe this physical neoteny is linked to behavioral traits like curiosity, playfulness, and flexibility, qualities that have helped humans adapt to a wide range of environments and challenges. But these differences don't exist in isolation. They're interconnected. Theory of mind enhances communication. Language amplifies the benefits of extended childhood, and the long developmental period gives humans time to master the complex social and cognitive skills that define our species. It's also important to recognize what doesn't make us unique: tool use. Chimpanzees make and use tools. Empathy, elephants mourn their dead. Problem solving, crows can figure out multi-step puzzles. What makes humans special isn't any single trait in isolation. It's the combination, the way these abilities work together and amplify each other. Humans aren't just smarter primates. We're a species that developed a unique cognitive toolkit, one that allowed us to build cities, write symphonies, explore space, and ask questions like, what makes us human? It's the ability to think about thinking, to communicate in layers of meaning, and to learn over a lifetime that has set us apart. Not better, not superior, just different. And that difference, small as it may seem in percentage points of DNA, has made all the difference in the world.